Hello, and welcome to the Snoozy Scientist. I'm really glad you made it here tonight. Wherever you are on this planet, this little pocket of quiet was made just for you. A calm space where science and stillness can sit side by side to put you to a peaceful sleep. Tonight, we're traveling back 42,000 years ago to a time when the Earth's greatest protector, its invisible magnetic shield, nearly disappeared. For billions of years, that unseen force has stood between life and annihilation, turning aside the endless radiation streaming from the sun and from deep space. Without it, oceans would thin into vapor, the air would slowly burn away. But then something changed. The field weakened, not a little, but by almost 90%. For a time, Earth was almost defenseless. The sun's radiation poured in more freely than it had in millions of years. The sky lit with curtains of red and green light, not just at the poles, but everywhere. Scientists call it the Laschamps Excursion, a magnetic collapse unlike anything in history. It happened while mammoths roamed across icy plains, while Neanderthals built fires in the dark, while the first humans left handprints on cave walls, unaware that the sky above them was changing. But what could cause a planet to lose its shield? What strange things happened to life under those glowing, dangerous skies? How did Earth recover, and could it happen again? Tonight, we drift back into that forgotten chapter to the time when Earth nearly lost its protection. But before we begin, if you're already feeling the calm, it would mean the world if you gave this video a gentle like, maybe even subscribed, if you'd like more sleepy science stories like this one. And if you'd be so kind, let me know in the comments, where are you winding down from tonight, and what time is it there? It always brings me joy to see how far these gentle science stories manage to ripple out across the globe. So now, take a slow breath, let your shoulders drop, and together, let's return to the moment when our planet's invisible guardian almost vanished. If you close your eyes for a moment and imagine the Earth from far above, floating like a blue lantern in a quiet sea of darkness, you might picture its oceans, its continents, its slow turning under the sun. What you would not see, no matter how closely you looked, is the soft halo that surrounds it. It is silent and weightless. It casts no glow and leaves no shadow, yet it has guarded life for more than 4 billion years. It is the magnetic field, a great veil shaped by an ocean of molten metal deep beneath our feet. Far below the crust and the mantle, past layers of stone shaped by heat and time, lies the outer core. It is made of liquid iron mixed with nickel. The temperature there is so high that solid metal becomes fluid and restless. It rises and sinks in slow spirals, stirred by heat from the inner core and by the turning of the planet itself. These motions create faint electrical currents, and those currents blend together into a single, larger field that reaches far beyond the surface. It is a simple idea at its heart. Moving metal gives birth to an invisible force that extends outward like a soft, steady breath. We rarely stop to think about this field because we cannot touch it or hear it, yet it shapes our days without asking for attention. When the sun sends out fast streams of particles, pieces of itself carried across space, they race toward our world like a tide of light that never reaches the ground. The field bends them away. Some are caught and funneled toward the poles, some slip into the magnetic pockets circling the planet, the zones scientists call the Van Allen belts. There, radiation gathers quietly, turning in loops far above us. Without this protection, sunlight would be harsher and far more dangerous. The upper layers of the atmosphere would thin. The surface would feel the raw energy of space. Even the simplest things rely on this shield. A compass needle turns because it listens to the field as gently as a leaf listens to the wind. Migrating birds follow quiet paths in the sky that their ancestors traced long before humans wrote maps. Certain bacteria swim in sediments, guided by the faint pull that threads through the planet. Every one of these moments, from the quiet turn of a compass to the journey of a bird over the sea, is shaped by something we cannot see. Life itself thrives because this barrier filters the world beyond. On other planets like Mars, the lack of a strong field left the air exposed. Over long stretches of time, the solar wind stripped its atmosphere away until only a thin layer remained. Earth is different because of the living core beneath us. It pushes outward with a protective strength that reaches across tens of thousands of kilometers, forming a bubble around the planet. Scientists call this bubble the magnetosphere. It stretches far toward the sun, pressed by the solar wind, and then trails behind the Earth like a long glowing tail that drifts into the deeper night. If we were to drift through this bubble in a ship that made no sound, the edges would feel like a gentle boundary between worlds. Particles streaming from the sun would be slowed, bent, and softened before they ever reached the air below. Some would spiral along magnetic lines and slip toward the poles, where they would create the auroras that bloom silently in the cold sky. Others would be held at a distance, turning endlessly around the planet like dancers in a wide, invisible ring. This graceful balance has allowed Earth to keep its oceans, its atmosphere, and the fragile chemistry needed for life to grow. When we walk through forests or sit beside the sea, there is no sign of the field. It does not shimmer or hum, yet it surrounds every leaf and wave, every mountain and desert. It reaches into quiet places where no person has ever stood. Even astronauts drifting above the world remain within its vast shelter. The scale is almost unimaginable. From the ground to the top of the magnetosphere, the distance is greater than any mountain multiplied many times. It is like standing inside a sphere so large that its walls fade out of sight. For most of human history, people sensed its presence without understanding its source. They saw the northern lights and felt the pull of lodestones, small magnets that pointed themselves in steady directions. They used that quiet guidance to cross seas and deserts, trusting a force that lies far beneath the surface. Only in recent centuries did we learn that this same force shields the Earth from storms that rage across space, storms no eye could see. This field feels constant, almost eternal, yet it shifts and sways with time. It grows stronger or weaker in places. The poles wander like travelers following some deep rhythm inside the core. Even with these gentle changes, the field continues to hold. It has always found a way to endure. As we move forward through this story, we will step deeper into the chapters where this shield faltered. For now, it is enough to rest within the thought that an entire world is wrapped in a protective embrace, created by the quiet motion of metal far below us, a motion that has kept life safe for longer than memory can reach. If we could drift downward through the layers of the earth as gently as a falling feather, we would pass through stone, warmed by ancient heat, then deeper still, into regions where rock softens and flows like thick honey. Far below all of that lies a hidden ocean, one made not of water, but of glowing metal. It moves with a slow and powerful grace. It is the outer core, a vast realm of liquid iron stirred by the heat of the inner core and by the turning of the planet. Every motion inside it shapes the world above, although no one standing on the surface ever sees a single ripple of this secret sea. The temperatures in this deep place soar so high that even metal loses its solid form. Iron becomes fluid, free to move in sweeping currents. These currents rise and fall, guided by heat that lifts lighter material upward and pulls cooler material downward again. This movement is sometimes compared to boiling water, yet the scale is so immense that even the simplest comparison feels too small. These currents drift slowly across thousands of kilometers, pushed and twisted by the rotation of the Earth. As they turn, they generate faint electric currents. These currents blend and stretch outward, forming a greater field that surrounds the whole planet. It is strange to think that something as gentle as the turning of molten metal can create the magnetic shield we explored earlier. Yet here in the dark center of the planet, the process unfolds every moment. Nothing about it is still. The currents shift where the heat is strongest. They twist into new shapes as the rotation of the planet changes their paths. Even the composition of the core adds its own layers of movement. Gradually, these overlapping motions transform into the magnetic field that extends around the Earth like a soft protective cloud. This hidden engine is often described as a dynamo. The word itself brings to mind the image of a turning wheel that creates energy from motion. Deep inside the planet, the same idea holds true. The rotation of the Earth guides the movement of liquid iron into spirals of motion. These spirals create electricity, and that electricity creates magnetism. It is a cycle that continues year after year, century after century. Because of that ceaseless movement, the field never remains fully steady. It wanders slowly, shifting its strength across the surface. The poles drift in quiet arcs, sometimes over short distances, sometimes over long ones. This drifting is so gradual that it becomes noticeable only when the changes accumulate over many generations of measurements. Even though the field feels stable when we hold a compass or watch the auroras, it is always in a quiet state of change. In some places, it grows weaker. In others, it grows stronger. It breathes in a way that mirrors the restlessness of the core itself. Over long stretches of time, the entire field can rearrange, weaken, or recover. These changes are part of a natural rhythm that has shaped the Earth's history for millions of years. Some shifts are gentle, others unfold during rare and extreme moments, the kind we approached at the beginning of this story. Those moments remind us how deeply the surface of the world is tied to the motions under our feet. Understanding this hidden realm is no simple task. No drill can reach the core. The pressures and temperatures would crush or melt any tool we send downward. Instead, scientists listen to the Earth itself. When earthquakes travel through the crust and mantle, they create vibrations that spread through the planet. These vibrations move differently through solid and liquid material. By studying how they travel, scientists can create images of the layers beneath us. It is similar to how physicians use sound waves to glimpse the inside of the human body. The Earth sends signals through its own layers, and with careful attention, those signals reveal shapes, boundaries, and motions that could never be seen directly. Through these echoes, scientists have discovered that the outer core is not uniform. It has currents that shift and swirl, places where heat rises and places where cooler material sinks. The inner core, though solid, may rotate slightly faster or slower than the rest of the planet, adding another layer of motion that influences the magnetic field. These patterns form a landscape that is always changing, though the changes unfold across timescales far longer than a human life. When we think of the Earth, it is easy to picture the surface alone, the oceans, mountains, and skies. Yet beneath everything we know, this deep metallic sea keeps moving. It sends its influence outward in ways we rarely notice, yet rely on every day. In the quiet of night, while forests rest and oceans breathe, the core continues its slow spinning dances. It generates the magnetic cradle that wraps around the planet. It carries memories of countless ages and keeps creating the force that makes compasses turn and shields the Earth from the storms of space. As we leave this deep place in our imagination and return gently toward the surface, the warmth of the core fades into softness. The hidden engine keeps turning far below. The world above continues to drift through space, held steady in its invisible embrace, shaped by a force born in darkness and carried upward through every layer of the earth. When we speak about the magnetic field and the way it shifts through time, it may seem like a story built from imagination, something too vast and invisible to ever leave a trace. Yet the earth, patient as always, keeps quiet records. It stores them in places that do not look like archives at all. They sit in stones shaped by fire, in soft layers at the bottom of ancient lakes, and in sediments that rest far beneath the waves. These records are written in iron, a metal that listens to the magnetic field with remarkable sensitivity. When iron cools or settles, it aligns itself with the direction of the field at that moment, almost like a compass needle freezing in place. Long after the surrounding landscape changes, that tiny orientation remains, quietly holding the memory of a time long gone. Scientists call this study paleomagnetism. It is the science of reading the Earth's ancient magnetic whispers. The word may sound complex, but the idea is gentle. Iron particles behave like tiny storytellers. They turn to face the magnetic field while they are still warm or suspended in water. Then, when they cool or settle into mud, they lock that direction into their structure. The stones formed from these materials carry the orientation with them for thousands of years, sometimes millions. By studying the way these particles point, scientists can reconstruct not only the strength of the magnetic field, but also where the poles sat in the sky as time passed. One of the first clues about the Great Magnetic Collapse came from volcanic rocks found in central France. In that region, ancient lava once flowed across the land, cooled in the open air, and hardened into dark stone. Over time, these flows stacked in quiet layers, each one a snapshot of the magnetic field that existed while the lava cooled. When researchers studied the iron inside these rocks, they noticed something strange. In some layers, the magnetic direction pointed almost entirely opposite to the modern one. In others, it seemed confused, as if the field had wandered wildly before settling again. These mismatched directions suggested not a gentle drift, but a moment of deep instability in the magnetic flow that rose from the core. Far from France, another set of clues rested under the ocean. At the bottom of the sea, fine particles fall continuously through the water. They drift slowly, settling into soft layers of sediment that build up over long stretches of time. Some of these particles contain iron. As they descend, they align themselves with the magnetic field that circles the Earth. Once they reach the ocean floor and become part of the growing sediment layers, they preserve that alignment. When long cores of this sediment are pulled upward through drilling missions, they reveal bands of ancient magnetic directions. If the field was strong, the particles line up clearly. If it was weak, their orientation becomes faint and scattered. These marine sediments showed something remarkable. Around the time of 42,000 years ago, the magnetic alignment nearly vanished. Instead of pointing strongly in a single direction, the iron grains appeared confused and disordered. They tilted in ways that suggested the field had lost its strength, almost as if it had dimmed to the faintest of glows. Ancient lake beds added another layer of evidence. Lakes often collect extremely fine sediments that settle like dust drifting through still air. These sediments preserve magnetic directions with impressive clarity. In certain lakes scattered across North America and parts of Asia, researchers discovered thin layers that captured the same strange patterns seen in the ocean. The iron particles recorded a moment of directionless magnetism, a time when the field weakened so much that even tiny grains had trouble deciding which way to face. Taken together, these rocks and sediments were like pages of a scattered diary. Each page recorded a different place, a different environment, yet all described the same unusual moment in the Earth's magnetic story. The field had not simply drifted or wavered, it had collapsed to a fraction of its former strength. Scientists then began comparing these magnetic signatures with other clues. Ice cores from the far south and far north, tree rings from ancient forests, and atmospheric markers all hinted at increased cosmic radiation during that same period. As the pieces came together, a clearer picture emerged. The magnetic field had nearly vanished, and the timing matched across continents, oceans, and climates. It can feel almost magical that something as fleeting as the direction of a magnetic field can be stored in stone. Yet these records have helped scientists trace magnetic reversals and collapses from deep in the planet's past. The signature from 42,000 years ago is one of the clearest of all. It marks a moment when the shield around the Earth faltered, leaving behind evidence across the world, like a soft imprint pressed into the planet's memory. In these quiet records written by iron, the Earth tells us that the collapse was real, that it happened everywhere at once, and that long before humans could measure such things, the planet had already lived through a moment of extraordinary change. There are moments in the history of the Earth when the deep engine beneath our feet shifts in ways so profound that the entire planet feels the change. Not through earthquakes or eruptions, but through something quieter, something woven into the invisible threads that stretch from the core to the sky. One of these rare moments happened long after the world cooled from its fiery beginning, but long before cities or written memory. Scientists call it the Laschamps Excursion. It was a brief wandering of the magnetic field, a temporary collapse followed by a sudden reversal, like a compass losing its certainty and then regaining it with its poles exchanged. The name comes from a small region in central France, a place where ancient lava cooled into stone and preserved the direction of the magnetic field that existed at that time. When researchers studied those rocks, they found that the iron inside pointed south, not north. It was as if the magnetic poles had traded places for a while. As more evidence appeared across the world, from lake sediments to seafloor mud, it became clear that this was not a local quirk. It was a global anomaly that touched every continent and ocean. The event began around 42,000 years ago, during a time when the world was home to mammoths, giant deer, and the last chapters of the Neanderthals. The magnetic field did not flip in a single instant. It weakened first, gradually at the beginning, then more sharply. Over the course of roughly 1,000 years, the field became unstable. Its strength faded until it was only a faint shadow of what it once had been. Scientists estimate that for around 500 years, the field hovered near its weakest state, so thin and fragile that it allowed streams of cosmic particles to reach the atmosphere almost unhindered. During this period, magnetic north wandered across the sky, drifting far from its usual place. Magnetic south did the same. They moved like travelers searching for a destination, and eventually each wandered into the position once held by the other. For a short time in geological terms, the world had its poles reversed. Compasses, had they existed then, would have pointed in the opposite direction. The field that wrapped around the planet reoriented itself before slowly rebuilding. Once the deep currents in the core settled into new patterns, the poles drifted back to their original positions. The magnetic field regained its strength over many centuries, as if exhaling after a long and troubled breath. Although the reversal itself was brief, the instability that surrounded it was long and complex. The core does not turn like a perfect wheel. It moves through rhythms that shift over thousands of years. During the Laschamps Excursion, these rhythms slipped into turbulence. Molten iron inside the outer core swirled into patterns that weakened the magnetic field. These patterns were not violent in the way we think of storms. Instead, they were subtle and deep, invisible to any creature living on the surface. Yet the consequences reached into the sky, affecting the atmosphere and the radiation that touched the Earth. The weakened field allowed more cosmic particles to enter the upper air. These particles collided with molecules high above the ground, altering the chemistry of the atmosphere in ways that researchers can still detect in ice and tree rings. At the same time, the auroras that usually shimmer near the poles bloomed across much wider regions, a sign of charged particles reaching latitudes where they rarely appear. The sky carried hints of the magnetic confusion below. The Laschamps Excursion did not last long when measured against the age of the Earth. In a timeline that stretches back billions of years, those few centuries are like a quick flicker of light, yet their memory remains clearly written in rocks scattered across the world. Volcanic basalt records the reverse direction. Ancient sediments hold layers where the iron grains point in strange and inconsistent ways. Together they show a moment when the magnetic field lost its strength, rearranged itself, and then slowly recovered. For early humans and the creatures that lived beside them, the reversal was not something they could name or measure. They would not have known the cause. They would only have seen the changes in the sky or felt them through subtle shifts in climate. To us, with the tools to read the magnetic traces preserved in stone, the Laschamps Excursion is a glimpse into the restless nature of the planet. It shows that the field is not fixed. It can sway, collapse, and rebuild. It can reverse entirely and then return to its usual orientation, guided by the deep and slow movements of molten metal far below the crust. As the field strengthened again after the excursion, the poles drifted back to their familiar places. The shield around the planet regained its form. The Earth continued its quiet turning, carrying within it the memory of that rare and turbulent moment when the sky and core seemed to speak in the same unsettled rhythm, and the world adjusted itself once more. When the magnetic field weakens, the change begins far above the world's surface, in a region where the air thins into silence and the sky opens toward space. Normally, streams of charged particles from the sun curve gently around the planet, guided by the magnetic shield we explored earlier. But during the long, quiet faltering that marked the Laschamps Excursion, the shield thinned until the air above the world lay almost bare. What followed was a transformation of the sky, a kind of ancient light show that no humans alive today have ever seen. Cosmic rays, usually deflected or softened by the magnetic field, slipped more easily into the atmosphere. They arrived from all directions, traveling from distant stars and from the sun itself. These particles collided with the molecules of the upper air, breaking them apart and sparking chains of reactions that reached downward through the sky. Where the field had once shaped and steered them, the weakened shield allowed them to dive deeper, touching layers of the atmosphere that rarely experience such activity. In those rare centuries, the sky must have carried an unusual brightness. Auroras that normally danced only near the poles spread outward like drifting curtains, pale at first and then shifting into reds, blues, and greens. They reached places where they had never been seen before, sweeping over Africa, Australia, and islands scattered through the vast Pacific. These shimmering lights would have glowed in places where warm nights usually hold only the stars and the soft patterns of cloud. They would have appeared across the tundra where mammoths grazed, and across the dark forests where early humans traced their steps by firelight. The glow itself would not have been constant. It would have pulsed with the rhythms of the solar wind. At times it would have faded almost to nothing, leaving nights quiet and dark. Then, when the sun released a stronger burst of particles, the sky would have shifted again into pale sheets of color, stretching from horizon to horizon. In some regions, the auroras may have trailed long, wavering streaks overhead, as though the heavens had become a great moving tapestry. Deep in the ice of Antarctica and Greenland, scientists have found the chemical fingerprints of these ancient sky storms. Layers of snow that fell during that time captured small quantities of radioactive isotopes that formed when cosmic rays struck the atmosphere. Two isotopes stand out clearly in these frozen archives: One is beryllium-10, a rare form of the element that forms when high-energy particles break apart nitrogen and oxygen in the upper air. The other is carbon-14, a form of carbon that becomes part of the atmosphere when cosmic rays collide with it. Normally, these isotopes occur at modest levels, increasing slightly during strong solar cycles and decreasing during quieter periods. But in the ice laid down during the Laschamps Excursion, both beryllium-10 and carbon-14 appear in sharp spikes. These spikes rise far above the usual background levels. They show that the atmosphere was bombarded with cosmic radiation at rates that do not match typical solar storms or ordinary fluctuations. The ice records are thin slices of time, each layer a quiet snowfall pressed into memory, and they reveal a world touched by far more cosmic activity than we experience today. These isotopes are not simply markers of light in the sky. They speak of deeper changes in the atmosphere. As cosmic rays penetrated further downward, they altered the chemistry of the air. They produced more of these rare isotopes because the weakened field could no longer shield the planet effectively. Even trees preserved this memory. Ancient tree rings from around the world show a sudden rise in carbon-14, a sign that the atmosphere itself was changed by the influx of cosmic energy. The increased radiation would have touched the surface indirectly. It would have changed the patterns of ionization in the upper atmosphere. It would have shaped the formation of clouds. It may have influenced weather in ways that unfolded slowly, like a long echo from the sky. Yet, for the people and animals living at that time, the most immediate change was likely the sky itself. The night would have felt different, as though woven with faint threads of color. Even the daytime sky might have carried unusual hues during periods of strong solar activity. In imagining that world, it is important to return gently to the thought that every part of this glow came from forces far above human sight. The weakened magnetic field allowed a deeper mixing between the planet and the currents of space. What we see in ice cores and sediments are the remnants of that mixing, preserved quietly through tens of millennia. They tell us that during those centuries of magnetic weakness, the Earth was exposed to the quiet but relentless rain of cosmic particles that normally stay at the edge of the atmosphere. As time passed, the field gradually regained its strength. The auroras retreated toward the poles. The cosmic bombardment softened. The isotopes returned to more familiar levels. Yet the memory of those skyfires remains in the layered ice of distant continents, in the slow growth of trees that lived through that ancient time, and in the stones that continue to hold the faint signatures of a world once lit by unusual and far-reaching light. As the magnetic field weakened and the sky opened itself to currents from space, the changes did not remain high above the clouds. Slowly and quietly, some of that energy filtered downward, touching the surface in ways that the world had not felt for a very long time. It was not a single wave or sudden strike. It was more like a long season of altered light, a subtle deepening of a force that is normally kept far away by the magnetic shield and by the thick blanket of ozone that hovers high in the stratosphere. Cosmic rays that once would have curved away from the Earth now slipped into the atmosphere with greater ease. Some broke apart molecules in the upper air and sent fragments drifting downward. Others reached deeper before releasing their energy. Under ordinary conditions, most of these particles never make it anywhere near the surface. But during the centuries of magnetic weakness that marked the Laschamps Excursion, a small but meaningful number did. For the animals and early humans who lived in those times, the air around them contained slightly more ionizing radiation than usual, a faint increase that came not from the ground or the rocks, but from the sky itself. The exposure would not have been instantly harmful. It would not have felt like a burn or a sudden illness. It was closer to standing beneath a sun that carried a sharper edge, a light that was almost the same, yet carried a little more bite in each ray. Over years and decades, this added radiation could influence the health of living things. Cells might have suffered more frequent damage. The subtle repair systems in the body, which usually keep pace with everyday wear, might have been stretched thin. One reason for this heightened exposure was ozone. The ozone layer protects life by absorbing much of the sun's ultraviolet radiation. When cosmic rays increased in number, they triggered chemical reactions that thinned portions of that protective layer. It did not vanish entirely, but in some regions it likely became patchy, weakened by chains of reactions started far above the surface. With less ozone, more ultraviolet light reached the ground. This type of light is invisible, but it can disrupt the delicate molecules inside living cells. During the centuries when the field was at its weakest, the world would have received more of it. Imagine a morning in that time. The light falling through the air would look the same as always. The colors of dawn would still spread across the horizon. The warmth on the skin would feel familiar. But inside every living cell, the energy carried by ultraviolet light and cosmic particles would create small tears in DNA, leaving marks that needed repair. For most creatures, the body's natural mechanisms would quietly fix the damage, yet as the exposure continued year after year, the strain would build. Some repairs would be imperfect. Some cells would fail to recover fully. These small changes, scattered across populations, could influence the health of future generations. When we think about solar storms today, we know that intense bursts of particles can reach the Earth during strong solar activity. These storms sometimes disturb satellites and power grids. They produce bright auroras and increase radiation levels near the poles. But even the strongest modern storms occur within the shelter of a magnetic field that still holds most of the sun's anger at bay. During the Laschamps Excursion, the field was far weaker. The effect was not a single intense storm, but a continuous exposure, similar in nature to modern events but magnified many times over and stretched across centuries. For animals living in open landscapes, the additional ultraviolet light could have influenced their behavior and their health. Furred creatures would have been somewhat protected, while those with bare skin or thin fur might have experienced more frequent skin damage. Birds migrating long distances under the open sky would have faced conditions subtly harsher than usual. Insects, which rely on delicate membrane wings and light-sensitive tissues, may have felt this change even more directly. The immune systems of many animals, including early humans, could have been affected as well. Increased radiation can weaken immunity over long periods. A weakened immune system does not fail suddenly. It simply copes less effectively with infections, leaving individuals more vulnerable to illnesses that would otherwise pass quickly. In small groups or isolated populations, this shift could influence survival, not through dramatic events, but through the quiet pressure of many small challenges. Ecosystems, too, may have felt the strain. Plants depend on sunlight, yet too much ultraviolet exposure can damage the surfaces of leaves and reduce growth. Some species adapt more readily than others, and in the long stretch of weakened magnetic protection, certain plants may have struggled while others thrived. These small shifts ripple outward through food webs. Herbivores respond to changes in vegetation. Predators respond to changes in prey. Even slight adjustments in ultraviolet light can influence growth cycles, reproduction, and the timing of seasonal behaviors. None of these effects would have reshaped the planet overnight. They unfolded in gentle but persistent waves. They left room for life to continue, for species to adapt and endure, but they also added stress to already challenging environments shaped by shifting climates and wandering ice. The world of 42,000 years ago was already in motion. The weakened shield and increased radiation simply added another layer to a landscape full of slow and interconnected changes. When the magnetic field eventually regained its strength and the ozone layer stabilized, the skies softened once more. The invisible pressure that had settled over the surface eased. Light returned to its familiar gentleness. Animals continued their quiet lives. Early humans kept painting on cave walls and walking through forests and plains, unaware that the sky above them had changed again. The marks left by that ancient radiation now rest only in ice, in sediments, and in the faint chemical signatures that tell the story of a time when the protective veil above Earth thinned and the ground below felt the touch of space a little more strongly than usual. When the magnetic field weakened and the sky filled with unusual light, the effects did not stop at the edge of the atmosphere. Slowly and almost silently, the climate began to shift. These changes were not uniform. They spread across the world like ripples in a wide lake, some gentle and some sharper, each influenced by the altered chemistry of the upper air and the delicate balance that governs the movement of heat, wind, and moisture. Scientists today look back at that ancient chapter by studying ice cores, lake sediments, and fossil pollen. These natural records preserve traces of the climate as it rose and fell across thousands of years. When they compare the timing of the Laschamps Excursion with these climate archives, the overlap becomes clear. The centuries when the magnetic field reached its weakest state match periods of sudden cooling in several regions, as well as shifts in rainfall and wind patterns that changed the way landscapes warmed and breathed. The increased cosmic rays that reached the atmosphere during the collapse did more than create glowing skies or leave behind rare isotopes. They played a subtle role in shaping the weather. When these particles collided with molecules high above the Earth, they created ions, tiny charged fragments that could act as seeds for cloud formation. Under ordinary conditions, clouds form when water vapor clings to dust or salt particles. But in a sky filled with more ions than usual, cloud droplets could form more readily, especially in colder regions where moisture hovered near the point of condensation. This process, though gentle, may have altered the amount and distribution of clouds around the planet. Clouds reflect sunlight back into space, cooling the surface below. With more ionization in the upper atmosphere, some regions may have experienced thicker or more frequent cloud cover. Even small changes in cloud behavior can influence temperature and wind patterns over long periods. What begins as a subtle shift in the heights and thickness of clouds can become a noticeable cooling across entire landscapes. In ice cores from Antarctica and Greenland, scientists have found evidence of cold intervals that align with the timeline of the weakened field. The snow that fell during those years carries chemical markers and trapped air bubbles that show slightly lower temperatures than the periods before and after. Each layer, laid down gently in winter storms, suggests that the planet was breathing in cooler rhythms for a time. Some regions experienced these changes more strongly than others. In parts of Europe and Asia, pollen records hint at shifts in vegetation. Plants that preferred warmer temperatures appear less frequently in sediments from that era. Trees that thrive in cooler climates become more common. These slow changes in forest composition suggest that the average temperatures dropped enough to influence which species grew well and which retreated. In other areas, drought patterns shifted. Some lakebeds show alternating layers of wet and dry conditions, as though storms and calm seasons traded places more quickly than before. The cause of these changes was not cosmic rays alone. The climate of the Earth is shaped by many forces working together. Ocean currents, volcanic activity, and long-term cycles in the planet's orbit also play roles in guiding temperatures and winds. But the overlap between the Lashamps timeline And these climate shifts suggests that the weakened magnetic field contributed to the mixture. The increased ionization in the atmosphere may have nudged the climate into new patterns, adding pressure to systems already in flux. In some regions, the shifts brought colder winters, wind patterns changed course, carrying Arctic air farther south. Certain parts of the southern hemisphere experienced different combinations of rainfall and drought. Over centuries, these changes would have influenced the lives of animals and early humans. Herds of grazing animals may have moved to track new growth in cooler or wetter grasslands. Hunters and gatherers may have found familiar landscapes becoming less predictable as weather patterns changed. On the other side of the world, ocean currents may have carried colder water into places that were usually warmer. This can affect how sea ice forms and melts, which in turn influences the air above. The interplay between ocean and sky is delicate. Even a slight shift can alter the timing of storms and the strength of seasonal winds. Although the cooling was not uniform everywhere, the pattern that emerges from these records is one of gentle disruption, not a single global freeze, but a set of regional changes that unfolded at the same time the magnetic field wavered. It was as if the planet passed through a phase of subtle atmospheric rearrangement, with cosmic rays acting as unseen participants in the process. As the centuries passed and the magnetic field slowly regained its strength, the climate began to settle again. Cloud patterns softened, ionization decreased, temperatures in many regions rose back toward their earlier levels. Forests and grasslands adjusted once more, growing into shapes adapted to steadier climates. The earth continued its slow turning, carrying forward the trace of these ancient shifts. The memory of that time now rests in ice, in rocks, and in the whispers of pollen preserved in quiet lake beds, each one a note in the long and gentle song of a planet that once moved through a moment of weakened protection and the climate changes that followed in its wake. Far above the earth, beyond the quiet blue of the sky and the thin shimmer of the upper atmosphere, lies the vast presence that shapes every day of our lives. The sun, a glowing sphere of plasma and light, warms the oceans and nourishes the forests. It pulls the planets through their orbits with a silent and unwavering force. Yet along with its warmth, it sends out streams of charged particles that sweep through the solar system like invisible winds. Under normal circumstances, the Earth's magnetic field bends these winds and softens their touch. But during times when that shield weakens, the balance between planet and star shifts in quiet but powerful ways. The sun is not a perfectly steady beacon. It moves through rhythms that last roughly 11 years, cycles in which it grows more active and then more calm again. During the active phase, called the solar maximum, the sun produces more sunspots, more flares, and more eruptions of charged particles. These eruptions are known as coronal mass ejections. They are vast clouds of plasma launched into space, each one carrying magnetic fields of its own. When these clouds reach Earth, they can disturb the magnetic field and trigger bright auroras in the polar skies. In our present age, even the strongest solar storms are softened by the magnetic shield that surrounds the planet. The field curves the incoming particles away, guiding many of them into the Van Allen belts or channeling them toward the poles where their energy paints the sky in waves of color. Satellites may feel the jolt of these storms, and power grids can be strained during the largest events, but life on the surface remains protected by the combination of the magnetic field and the thick layers of atmosphere below it. During the centuries of the Laschamps Excursion, this protection was far less certain. With the field weakened to a fraction of its normal strength, the sun became a much more influential presence. Even ordinary solar winds would have reached deeper into the magnetosphere, brushing the atmosphere more directly. And if a coronal mass ejection had occurred during those weakened years, its impact would have been far greater than it would be today. To imagine the difference, picture the Earth encased not in a firm magnetic bubble, but in a thin and fragile shell. When a solar storm arrives under normal conditions, the magnetic bubble absorbs much of its energy. But during the Laschamps Excursion, the bubble would have sagged and flexed, its boundaries pushed inward toward the planet. More charged particles would have slipped inside, spiraling toward the upper atmosphere and stirring chemical reactions that left subtle imprints in the air. These storms may also have intensified the glowing skies described earlier. With the field weakened, solar particles would have entered regions far from the poles, creating auroras that stretched across continents in colors that rarely appear today. They would have illuminated the night with reds and greens, hues that flickered through the dark and reflected quietly off lakes and ice. The interplay between the sun and the collapsing field likely affected the climate as well. Solar storms can influence atmospheric circulation by warming or ionizing the upper layers of air. Under a stable magnetic field, these effects are limited and short-lived. Under a weakened one, the same events could have contributed to longer-lasting changes, layering themselves onto the subtle cooling and shifting weather patterns already unfolding at the time. The sun's influence reaches deeper than light and warmth. Its magnetic storms can compress and reshape Earth's own magnetic lines. When the field is strong, this reshaping is temporary and mild. When the field is unstable, these interactions can be more chaotic. Magnetic north and south were already wandering during the Laschamps Excursion. Encounters with strong solar winds could have encouraged even more drift, stirring the play core's influence on the field into patterns that shifted over decades rather than centuries. To early humans, the sun during this time may have seemed unchanged. It still rose and set across the horizon, still warmed the land by day, but something in the sky's behavior may have felt different. At times, there might have been a brightness at night that followed periods of strong solar activity. During intense storms, colors may have shimmered even where the population had never seen such lights before. The sun's storms, invisible to the eye until they touched the atmosphere, would have played their part in the long story of the weakened magnetic shield. As centuries passed and the field regained its strength, the sun resumed its familiar role as a steady guide of seasons and climates, its storms softened once more by the invisible shield. Yet the memory of that earlier interplay remains locked in the Earth's archives. In ice and stone and ancient tree rings, we find the subtle marks of a time when the sun and the magnetic field touched each other more directly, shaping a world that glowed, cooled, and shifted in response. In that long-forgotten chapter, the Earth experienced not only the trembling of its own internal engine, but also the amplified breath of its star, a double influence carried across centuries of quiet and continual change. Deep in the frozen heart of the polar regions, where the wind moves in long sweeping strokes and the landscape rests beneath layers of ancient snow, the Earth keeps one of its most delicate archives. Every winter, a thin sheet of snow settles gently on the continent of Antarctica and across the vast expanse of Greenland. Each sheet becomes a page in a record that stretches back tens of thousands of years. Over time, the weight of new snow presses the older layers into ice, sealing away tiny bubbles of air, faint chemical traces, and the quiet memory of the atmosphere that once drifted above. When scientists drill deep into these ice sheets, the cores they pull upward look like long, pale cylinders of time. Layer by layer, they reveal stories frozen into place. Most years leave behind subtle patterns, the normal rise and fall of seasons. But some layers are marked differently, touched by forces that reach beyond the Earth. The centuries of the Laschamps Excursion are among them. During the weakened magnetic field of that ancient time, cosmic rays streamed into the atmosphere far more freely than usual. When these high-energy particles struck molecules in the upper air, they created rare isotopes that fell through the sky and became trapped in snow. One of these isotopes is beryllium-10, formed when cosmic rays break apart nitrogen and oxygen atoms. Another is carbon-14, created in a similar way when cosmic particles interact with carbon in the atmosphere. In the ice cores from both Antarctica and Greenland, the layers that correspond to roughly 42,000 years ago contain unusually high amounts of these isotopes. The spikes stand out sharply, rising above the levels recorded in the centuries before and after. They act like bright threads woven through the ice, marking a moment when the planet was touched more directly by the energy of space. Beryllium-10 is particularly helpful because it settles into the ice soon after it forms. When scientists examine these cores, they see a sudden upward leap in beryllium-10 concentrations during the period of magnetic weakness. This leap mirrors the same strange patterns seen in marine sediments and volcanic rocks, linking the atmospheric changes to the collapse of the field. The ice becomes a quiet witness, confirming the story told by stones and oceans. Carbon-14 tells a similar tale, but in a more delicate voice. When cosmic rays create carbon-14 in the atmosphere, it bonds with oxygen and becomes carbon dioxide. Plants absorb this carbon as they grow. Trees, in particular, lock it into their rings year after year. Because of this, tree rings form another archive, one built not from ice but from living wood that holds the chemistry of ancient air. When researchers compared the carbon-14 levels in old tree rings with those in the polar ice cores, they found something remarkable. The spikes in the ice matched perfectly with spikes in the wood. Trees growing in distant regions, far from the poles and far from each other, all showed a sudden and unusual rise in carbon-14 at the same moment. The ice recorded an increase in beryllium-10. These two signatures together form a kind of cosmic fingerprint, a clear indication that the entire planet was bathed in heightened cosmic radiation. Some tree rings even show slight irregularities in their widths, suggesting that the changes in the atmosphere may have influenced growth patterns. Not all trees responded the same way. Some continued growing steadily. Others formed narrower rings, hinting at shifts in sunlight or climate during those centuries. Yet the shared carbon signature tells us that all of them breathed the same altered air. When scientists place the ice records and the tree ring data side by side, the timeline becomes unmistakable. The Laschamps Excursion left its mark not only on rocks and sediments, but also on the very chemistry of the sky. The isotopes created by cosmic rays drifted through the atmosphere, settled into snow, and wove themselves into the wood of ancient forests. These traces survived long after the weakened field recovered and the skies returned to their calm blue. To hold a piece of ice core from that era is to hold a fragment of ancient air. Tiny bubbles inside the ice contain samples of the atmosphere as it existed then, untouched by time. When they are brought to the surface and warmed slightly, the bubbles release gases that have not moved in tens of thousands of years. Some of these bubbles include increased levels of the isotopes that hint at a world under a different kind of sky. A sky lit by expanding auroras and shaped by stronger flows of cosmic particles. These frozen records help scientists understand not only the timing of the magnetic collapse, but also the scale of its effects. They show that the spike in cosmic radiation was global, not regional. They reveal that the atmosphere itself changed in ways that can be measured even now. And when read alongside ancient trees, they show that life on the surface, no matter how distant or quiet, was touched by the same long pulse of cosmic influence. In the stillness of the polar ice, the Earth preserved the memory of those unusual centuries. The layers remain stacked in gentle rhythms, each one a whisper of the world that once was. Through them, we glimpse the story of a planet that faced a moment of weakened protection and quietly recorded every change in air, sky, and sunlight until the magnetic field gathered itself again and the Earth continued its slow and steady turning. Far beneath the drifting lights of that altered sky, early humans and Neanderthals moved through their world with the same quiet determination that had carried their ancestors across continents. They did not know about magnetic fields or cosmic particles or the slow turning of molten iron deep beneath the crust, yet they lived through the consequences of those unseen forces. Their days unfolded under a sky that changed in ways no one could explain, and their nights were lit by colors that once belonged only to the far northern and southern horizons. The world of 42,000 years ago was a place of shifting climates and vast open landscapes. Herds of mammoths wandered across frozen grasslands. Woolly rhinoceroses pushed through snowdrifts. In forested valleys, groups of Neanderthals gathered around fires, shaping tools from stone and bone. Early humans, who had already begun spreading into Europe, Africa, and Asia, painted scenes of hunts and animals on cave walls, unaware that the air above them held traces of cosmic events. During the centuries when the magnetic field weakened and the atmosphere changed, the sky would have carried a strange beauty. Auroras that normally danced at the edges of the world spread across entire continents. Red arcs might have risen above the plains where early humans hunted reindeer. Pale green curtains may have rippled above desert dunes. In forests, where branches filtered the night sky, the lights could have shimmered softly through the leaves, turning shadows into moving patterns. Such sights, appearing far from their usual homes, would have been mysterious, perhaps unsettling, yet impossible to ignore. These lights would have appeared more often and more brightly during strong bursts of solar activity. To the people living then, they would have seemed like signs from the sky. Some communities may have viewed them as omens. Others might have admired them in silence, watching the horizon glow in colors that had never washed across their nights before. Alongside these changes in the sky, the weakened field brought subtle shifts in health. Increased ultraviolet light and a slightly higher level of radiation reaching the ground would not have caused sudden sickness, but over years they could have added to the pressures faced by small populations. Skin irritation might have become more common during long days in the open. Weakened immune systems could have made people more vulnerable to infections that might otherwise have passed gently. These effects were mild on a moment-to-moment scale, but persistent enough to influence life over generations. Neanderthals, who lived mostly in small, scattered groups, may have felt these pressures more sharply than early humans. Their populations were already limited, and their territories were often located in regions prone to cold and shifting climates. As temperatures wavered and weather patterns changed, hunting grounds may have become less predictable. The animals they depended on could have migrated earlier or later than expected. Plant resources may have shifted with the climate, altering the landscapes they knew. Whether the weakened magnetic field directly affected their survival is still unknown. Scientists can see the overlap in time, but not a clear line of cause and effect. The disappearance of Neanderthals happened near the later part of the Lashamps period, a moment when the weakened field, cooler climates, and human expansion all converged. It may have been coincidence. It may have been one factor among many. The pressures of changing weather, competition for resources, and small population sizes already placed Neanderthals in a fragile situation. The added stress of altered skies and subtle shifts in atmospheric chemistry might have nudged that balance further. Yet these ancient people were observant. They would have noticed the changing colors in the sky and the way animals behaved differently as the climate shifted. They would have adapted where they could, moving shelters, adjusting hunting strategies, seeking new sources of food. They did not know the reason for the changes above them, but they lived through them with the resilience all early humans carried. Imagine a small group gathered at the mouth of a cave one night. A fire crackles softly near them. Above the dark treetops, a band of red glows across the sky, brighter than any sunset and lingering long after the sun has disappeared. Children point upward. Hunters grow quiet, listening to the crackle of the flames and the faint rustle of the wind. No one speaks for a moment. The light moves like something alive, rising and falling in the distance. To them, it is a mystery without explanation, a shift in the world that they can only witness, not understand. Across other regions, early humans may have noticed that some people fell ill more easily during certain seasons. They may have adjusted their movements, seeking shelter in caves or forests where the sunlight filtered softly through branches. They may have watched the animals they hunted grow scarce in areas that had once been plentiful. Life at that time already demanded adaptation, and the weakened field added new layers of quiet challenge. Despite these difficulties, humans survived and spread. They painted on cave walls, leaving handprints that still remain today. They crafted tools that reveal their skill and creativity. Their stories are preserved not in written words but in artifacts, in bones, in the traces of fires that still darken cave ceilings. Those stories unfold under the same sky that changed during the Laschamps Excursion, a sky that glowed with strange colors while they lived, traveled, and faced the complexities of their world. The traces of their experiences linger in the archaeological record, written in the things they left behind and in the timing of their movements across continents. Their world was shaped by many forces, some visible and immediate, others silent and unfolding far above the clouds. In this chapter of Earth's history, humans and Neanderthals moved beneath a sky touched by space, surviving in a landscape that was shifting gently around them, guided by changes they could not name, yet lived through one day at a time. As the centuries of magnetic weakness unfolded and the climate shifted in quiet but persistent ways, one of Earth's most enduring human lineages approached its final chapter. The Neanderthals, who had survived ice ages, harsh winters, and countless changes in their environment, began to vanish from the archaeological record. Their disappearance has long been a mystery. No single cause stands out with certainty. Instead, it appears like a tapestry woven from many threads, each subtle on its own yet powerful when intertwined. Among these threads are the environmental pressures that settled over the world during the Lashamps period. The increase in cosmic radiation, the thinning of the ozone in certain regions, and the shifting temperatures that followed would not have been instantly catastrophic. They would have acted gently, steadily, adding strain to lives already shaped by wild landscapes and unpredictable seasons. For small populations, even slight challenges can accumulate across generations. In ways that matter deeply, Neanderthals lived in smaller and more isolated communities than early Homo sapiens. Their populations spread across Europe and parts of Western Asia, but they remained relatively low in number. In some valleys, they formed small family groups, returning to the same caves and hunting grounds through changing seasons. Their lives were rich in culture and skill, yet their limited numbers made them more vulnerable to the slow pressures of environmental change. The weakened magnetic field allowed more radiation to reach the surface. The increase was not dramatic enough to cause sudden illness, but it may have created additional stress over time. Cells repairing themselves more often, immune systems working slightly harder, young individuals perhaps more susceptible to infections that early humans with larger population networks could recover from more easily. Even small shifts in health can influence survival, when a community's numbers are already fragile. Climate changes brought further pressure. In the centuries surrounding the Laschamps Excursion, some regions cooled more sharply than others. Forests shifted in composition. Animal migrations changed. Hunting patterns that Neanderthals relied on may have become less predictable. A landscape they knew well became a landscape in motion. Early humans faced the same changes, but their larger social networks and wider ranges gave them greater adaptability. They traded tools and resources. They moved more frequently. They joined with other groups when needed, creating diverse communities that could absorb challenges more easily. Genetic evidence now reveals that early Homo sapiens and Neanderthals met and interbred in several regions. Some of the ancient DNA carried by modern humans comes from these encounters. Yet the genetic record also shows that Neanderthal numbers were dwindling long before the final contact. Their genetic diversity was low. Many individuals shared surprisingly similar markers, a sign that their population size had been small for a long time. Small populations are more susceptible to shifts in climate, disease, and environmental changes, even those as subtle as increased ultraviolet exposure. The timing of their decline overlaps closely with the weakened magnetic field, the increased cosmic radiation recorded in ice and tree rings, and the climate changes that unfolded during that era. This overlap does not prove that the Laschamps Excursion caused their disappearance, but it suggests that the Neanderthals lived through a moment when the world around them was shifting in multiple ways at once. Cooler temperatures, changing prey availability, altered seasons, and above it all, a sky that glowed with unfamiliar colors. The presence of early humans added another layer of complexity. Homo sapiens had begun spreading widely, carrying new tools, new hunting strategies, and flexible ways of living that allowed them to adapt to environments both warm and cold. Their arrival did not immediately push Neanderthals aside, but over time, their growing numbers and diverse networks created competition in some regions and cooperation in others. In places, they shared caves. In others, they exchanged knowledge. The archaeological record shows moments of overlap, hints of cultural exchange, and the merging of lineages that left traces still detectable today. Yet, even with these connections, Homo sapiens ultimately outlasted Neanderthals. Their populations grew, while Neanderthal numbers dwindled. Their genetic diversity increased, while Neanderthal diversity shrank. As the magnetic field gradually strengthened again and the skies softened, early humans continued to spread across Europe and Asia. Neanderthals, already limited in number, appear to have vanished sometime after the magnetic field reached its lowest point and began its slow recovery. The overlap in timing invites questions. Did the increased radiation weaken Neanderthal immunity just enough to make illness more dangerous in small groups? Did climate changes alter the availability of prey animals they relied on? Did early humans simply outnumber them in the long run, taking advantage of changing conditions more quickly? Or were the pressures of the Laschamps Excursion one part of a larger story, a quiet influence adding weight to challenges already unfolding? No single answer stands alone. The decline of the Neanderthals seems to have been shaped by a combination of environmental stress, limited population size, and competition with a closely related species that adapted with remarkable flexibility. The weakened magnetic field was not the cause, but it may have been one of many forces that nudged the balance toward change. What remains today are their traces. Tools shaped by hands that lived through nights lit by strange auroras, bones that hold stories of hunting, shelter, and survival. DNA woven into the genomes of modern humans, a gentle reminder that they were not entirely lost. They walked the earth during a time of cosmic and earthly transformation, enduring as long as they could beneath skies touched by colors and forces they could not understand. Their disappearance marks one of the quiet turning points in the long story of our planet, shaped by both the deep earth below and the vast heavens above. Across the wide plains of the ancient world, long before cities or roads or the familiar shapes of modern animals, great herds of megafauna moved with the rhythm of the seasons. Mammoths trudged slowly across frozen grasslands, their breath rising in pale clouds. Giant deer lifted antlers as wide as branches. Woolly rhinoceroses scraped through snow to uncover hidden plants. The world they knew was a place of shifting ice, open tundra, and cold winds that shaped every part of their lives. During the centuries when the magnetic field weakened and the atmosphere began to behave differently, these great animals faced a landscape that was changing in ways too subtle for them to recognize, yet too persistent for them to escape. The climate fluctuations that unfolded during the Laschamps period created new pressures that rippled through the ecosystems of the Northern Hemisphere, touching the lives of every species that depended on the balance of cold and warmth, the increased cosmic rays that entered the atmosphere during the weakened magnetic field subtly altered cloud behavior, and with that came shifts in regional temperatures. Some places cooled more quickly than expected. Glacial ice crept outward from the high mountains and polar regions. Snow lingered longer in spring. Winters grew sharper in certain valleys and plains. Even small drops in temperature could influence the availability of plants, the depth of snow cover, and the timing of seasonal migrations. Mammoths were among the best adapted creatures of this age. Thick coats of fur insulated them from the cold. Layers of fat helped them endure long winters with little food. Their massive size conserved heat, allowing them to withstand temperatures that would challenge smaller animals. Yet adaptation did not mean invulnerability. When winters grew longer and summers shorter, plants that mammoths relied on for food sometimes failed to grow in the abundance they needed. A thin summer meant less fat stored for winter. A harsh winter meant more energy lost, searching through deeper snow. In regions where cooling was most pronounced, grasses gave way to shrubs or vanished beneath persistent layers of ice. Mammoths could migrate, but only to a point. Some herds likely shifted their ranges southward. Others stayed in familiar regions, but faced more difficult conditions at the edges of the growing cold. Their population sizes rose and fell with the rhythm of the climate, responding to each new challenge with the same slow resilience that had carried their kind through earlier ice ages. Other megafauna faced similar struggles. The woolly rhinoceros, with its dense fur and heavy build, thrived in cold environments, yet it relied on specific types of vegetation that could disappear when seasons shifted even slightly. The giant deer, whose magnificent antlers required rich plant growth to support their development, may have suffered when colder years reduced the availability of the nutritious grasses and herbs they depended on. Cave lions and hyenas, predators that followed the herds, were affected indirectly. When prey populations fell or moved unpredictably, they too faced harder conditions. The weakened magnetic field likely played only a subtle role in these climatic changes, yet even subtle influences can matter when layered onto natural cycles already in motion. As cloud patterns shifted due to increased atmospheric ionization, the spread of sunlight across certain regions changed. Some areas became cooler, helping glaciers expand. Glaciers are powerful shapers of climate. When they grow, they reflect more sunlight, keeping temperatures even lower. This feedback loop can intensify cooling in nearby regions, reshaping entire landscapes over centuries. In valleys where megafauna grazed, glaciers may have pushed downward into places that once supported summer growth. Rivers fed by melting ice could change their paths, altering wetlands or draining regions that had been lush. As ice sheets thickened, the air above them cooled further. Winds sweeping down from these icy heights carried cold into regions that had once been more temperate. These changes did not spread evenly across the world, but where they took hold, they influenced the fate of every creature living there. For early humans and Neanderthals, these shifts were challenges they could respond to through movement and adaptation. But for megafauna, whose survival depended on stable access to vast areas of food, climate change altered the relationship between land and life in ways that tested their long-standing resilience. Their size, which was once an advantage, became a burden when food grew scarce. Calves born during lean years had lower chances of surviving. Herds fragmented when resources dwindled. The pressures were not the same everywhere. Some regions remained hospitable, and in those places megafauna continued to thrive through the weakened field and the fluctuations that followed. But the broader pattern was one of increasing stress. The world was shifting toward colder cycles driven by larger climatic rhythms that had begun long before the magnetic field collapsed and that would continue long after it recovered. The Lashamps period added another layer to these changes, a gentle push that helped tip certain regions toward deeper cold. For the animals themselves, life continued one day at a time. Mammoths still gathered by rivers, breaking through ice with their tusks to drink. Giant deer still wandered the edge of forests, heads held high as the seasons turned. Packs of wolves still followed the herd trails through snow, softened by early dawn light. None of them knew they were living through a time of subtle planetary transformation. They simply followed ancient instincts etched into their bones. These creatures would persist for thousands more years after the Laschamps Excursion, but the seeds of their eventual decline were being planted in these centuries of atmospheric change and shifting ice. For now, though, they remained the giants of their world. Their shapes moved across the frozen plains like shadows cast by an ancient age, carrying with them the quiet strength that had seen them through countless winters, even as the cold deepened in slow, steady breaths around them. Deep within the trunks of ancient trees, long before they toppled to the forest floor or fossilized into stone, the air of the past waited in silence. Each tree ring held a thin layer of carbon drawn from the atmosphere during a single year of growth. Most years left behind a balanced and steady mix of carbon that matched the normal rhythms of sunlight, seasons, and air. But during the centuries of the Laschamps Excursion, this balance shifted in a way that can still be traced today, a quiet chemical fingerprint left by a world touched by unusual amounts of cosmic radiation. To understand this mystery, it helps to picture the flow of carbon in the natural world. Carbon travels between the air, the oceans, the soil, and all living things in a slow cycle that stretches across time. Plants absorb carbon dioxide from the air as they grow, weaving the carbon into their leaves, trunks, and seeds. Animals eat the plants, carrying the carbon forward. When plants and animals die, their carbon returns to the ground or the air. Through all of these exchanges, the total amount of carbon-14 in the atmosphere remains small and fairly stable. Carbon-14 is a rare form of carbon that behaves just like the ordinary kind, except for one important detail: it is created in the atmosphere by cosmic rays. When high-energy particles from space strike nitrogen molecules in the upper air, they create small amounts of this radioactive carbon. Plants absorb it along with ordinary carbon, and because it decays slowly over time, it becomes a natural clock inside anything that once lived. During the Laschamps Excursion, when the magnetic field grew weak and the atmosphere allowed more cosmic rays to penetrate, the creation of carbon-14 increased dramatically. This was not a small shift. Tree rings from around 42,000 years ago show a sharp rise in carbon-14, unlike anything in the centuries before or after. It is as though the atmosphere suddenly changed. Flavor, and the trees recorded that change with perfect, quiet honesty. When scientists first studied these ancient rings, the pattern seemed unusual but not fully understood. It was only when they compared the rings from different continents that the magnitude became clear. Trees in Asia, Europe, Australia, and the Americas all showed the same sudden spike. In some places, this increase lasted for decades. In others, the shift was slightly shorter, reflecting the local climate and the lifespan of the trees. But the timing was consistent across the world. The atmospheric change had been global. This rise in carbon 14 was not linked to volcanic activity or changes in ocean chemistry. The only force capable of increasing carbon 14 so sharply was cosmic radiation. And since cosmic radiation increases dramatically when the magnetic field weakens, the spikes in tree rings became one of the clearest signs that the Laschamps Excursion was unfolding at that time. The elevated carbon 14 had other effects too. It entered the oceans through the surface waters, where it mixed with dissolved carbon and spread through marine ecosystems. Shells and corals that formed during this period captured the same chemical changes. Sediments laid down in coastal regions preserved faint traces of the increased carbon 14, adding more layers to the global record. The entire carbon cycle, from air to forest to ocean, carried the signature of a sky more open to the universe. Because carbon 14 decays at a steady rate, scientists can measure it in ancient wood and calculate precisely when each tree ring was formed. The sudden increase during the Laschamps period created a distinctive marker that stands out from the natural fluctuations of earlier and later centuries. For this reason, the carbon 14 spike became a powerful tool for dating archaeological sites, climatic events, and fossils from that era. When researchers find preserved wood, charcoal from dye, ancient fires, or bones with traces of ancient carbon, they can match their carbon 14 levels to the spike in the global record. This discovery allowed scientists to pinpoint the timing of the Laschamps event with remarkable accuracy. Before this, the magnetic reversal had been known only through paleomagnetic studies of rocks and sediments. Those records were precise in direction, but less precise in time. The tree ring evidence, however, provided an annual record. By counting rings backward from known historical dates, researchers linked the carbon 14 spike directly to the weakening and reversal of the magnetic field around 42,000 years ago. In this way, the trees became storytellers of the ancient world. Their rings revealed not only the life they lived, but also the state of the sky above them. The increase in cosmic radiation left a mark in their wood that carried across millennia. When scientists placed these clues beside ice core records showing matching spikes in beryllium-10, the full picture came together. The timing, the cause, and the global reach of the event became clearer. What begins as a quiet chemical change inside a growing tree becomes, over tens of thousands of years, a guide to understanding one of the most dramatic magnetic shifts the Earth has ever experienced. The carbon 14 mystery is not just a puzzle of chemistry, it is a bridge across time, connecting the forests of the ancient world to the questions we ask today. The trees did not know they were recording the signature of a cosmic storm. They simply reached toward the sun, drank in the air around them, and built their rings year after year. Yet in doing so, they created a record so precise that it allows us to read the history of the atmosphere like the pages of a slow and gentle book. Through their quiet growth, the story of the Laschamps Excursion found one of its clearest and most lasting traces. Far beneath our feet, in the deep and restless heart of the planet, the Earth's magnetic story is being written every moment. It is a story shaped not by wind or water or shifting continents, but by the motion of molten metal drifting in slow, powerful currents around the solid inner core. This movement creates the magnetic field that surrounds the Earth, Yet the same movement also carries within it a quiet unpredictability. Over long spans of time, the flow of this inner ocean can become tangled and confused, and when it does, the magnetic poles begin to wander. On rare occasions, they drift so far and so chaotically that the entire field rearranges itself in a reversal. To imagine how this happens, it helps to picture the liquid outer core not as a smooth river, but as a storm. Heat rises from the inner core, pushing lighter material upward. Cooler material sinks back down. The turning of the earth twists these motions into spirals. Together they create patterns that continually shift, merge, and break apart. This chaotic movement generates electrical currents, and those currents create magnetic lines that stretch outward into space. When the flow remains steady, the magnetic field stays stable, but when the flow changes shape, the field begins to waver. Reversals happen when these deep currents lose their familiar rhythm. The magnetic field does not flip like a switch. Instead, it enters a turbulent phase where north and south weaken, drift, and sometimes disappear entirely for a time. In the absence of a clear direction, smaller magnetic patches appear across the surface, each with its own orientation. Some point north, others south, like tiny scattered magnets trying to decide which way the world should turn. Eventually, one of these patterns grows stronger than the rest and becomes the new dominant field. Sometimes it points in the opposite direction from the original one. When that happens, a reversal is complete. These shifts unfold slowly on the scale of a human life. A full reversal can take thousands of years. It begins with a long weakening, followed by a period of magnetic confusion, and then a slow strengthening as the new orientation settles into place. During this time, the Earth still spins, the winds still blow, and life continues. But the sky and the atmosphere can behave differently, just as they did during the Laschamps Excursion when the field nearly vanished for centuries. Reversals are natural parts of the planet's history. The magnetic field has flipped many times since the Earth formed. In the rocks beneath the oceans, stripes of cooled lava record each reversal like pages in a long chronological book. Some intervals between them lasted only a few 100,000 years. Others stretched across millions. There is no strict pattern, no steady clock that marks the timing of these events. The core behaves like a living system, guided by forces that move on scales far bigger than any we can see. Because of this irregularity, reversals are difficult to predict. Scientists can measure the strength of the current field, track the movement of the magnetic poles, and observe changes in the intensity across the planet. These measurements tell us how the field behaves today. They show that the poles drift slowly, that some regions weaken while others strengthen, and that the magnetic shield breathes through cycles of change. But they do not reveal when the next reversal will happen. Some reversals occur during times of great internal turbulence. Others begin quietly, with only slight weakening at first. In some cases, the field recovers without flipping, returning to its original state after a period of instability. The Laschamps Excursion itself was one of these temporary events. The field reversed briefly, but then returned to its earlier orientation, recovering strength once the inner currents regained their balance. It was a reminder that the magnetic field is both resilient and unpredictable, capable of dramatic rearrangements, yet always anchored to the deep processes of the core. Though reversals are global in effect, they are not catastrophic in the geological sense. Species have lived through them countless times. The Earth does not lose its atmosphere. The oceans do not boil. Instead, the changes unfold gradually, allowing life to adapt in small steps across generations. The most noticeable effects arise when the field weakens significantly during the transition, allowing more cosmic rays to reach the upper atmosphere. But even then, the planet continues its long journey through space, carrying life with it as it has for billions of years. When we look at the Earth today, with its magnetic poles drifting across the Arctic and the South Atlantic anomaly growing slowly over the oceans, we see hints of the field's dynamic nature. These changes do not guarantee a reversal, but they remind us that the magnetic field is alive in its own way, shaped by a core that never stops moving. The science of magnetic reversals is a study of deep time, of forces that move too slowly for any one lifetime to witness in full. Yet, it is also a study of resilience. The Earth has reversed its magnetic field many times. It has regained its strength every time, and through each cycle, life has continued, adapting quietly beneath skies that hold the memory of every shift and every breath of the planet's hidden dynamo. The story of the Earth's magnetic field does not end in the distant past, sealed within rocks and ice. It continues quietly in the present, shaping every day and night, even though most of us move through our lives without noticing its presence. The same deep currents of molten iron that once drifted into confusion during the Laschamps period still turn beneath our feet. They still rise and swirl around the inner core, carrying the patterns that guide the invisible shield around the planet. And just as in ancient times, those patterns shift. Over the last 2 centuries, scientists have measured a steady weakening of the magnetic field. The strength of the field has decreased by about 10% in that span of time. 2 centuries may seem long for us, but for the magnetic field, it is only a moment, the blink of an eye in geological time. This gradual decline has raised gentle questions rather than immediate alarm. It does not signal an imminent reversal or collapse, but it serves as a reminder that the field is always changing, breathing its slow and ancient rhythm. Modern instruments, scattered across the globe and drifting in satellites above the Earth, allow scientists to see the field with a clarity earlier generations could only imagine. Through these tools, a particular region has become a focus of attention. It lies over parts of South America and the South Atlantic Ocean. Scientists call it the South Atlantic Anomaly, a broad area where the magnetic field is weaker than in surrounding regions. In this place, the protective shield dips closer to the surface, allowing more charged particles from space to brush against the upper atmosphere. To the people living beneath it, the anomaly is invisible. The sky looks the same. The air feels no different. But satellites that pass overhead experience its presence directly. Some instruments become more vulnerable to interference. Radiation levels rise slightly inside their electronic systems, causing occasional glitches or shortened lifespans for sensitive components. When satellites enter this region, their operators often switch certain functions off, allowing them to drift quietly until they move beyond the weaker field. The anomaly is not a hole in the magnetic field, nor is it a danger to life on the ground. Instead, it is a sign that the field is shifting unevenly, growing weaker in some places while remaining steady or strengthening in others. These irregularities arise naturally from the complex flow of molten iron in the outer core. In some areas, the currents produce strong magnetic lines. In others, they counteract each other, leaving patches where the field grows faint. The South Atlantic anomaly is one of these patches. Scientists study it carefully because its behavior may offer clues about the future of the magnetic field. If the anomaly continues to expand or deepen, it could suggest that the field is entering another long period of change, not necessarily a reversal, but perhaps a phase of drifting poles and shifting strengths similar to earlier periods seen in paleomagnetic records. At the same time, the anomaly could simply be part of the natural variability that the field has always shown. The magnetic field has shifted countless times, growing stronger and weaker across millions of years without entering full reversal. The present changes may be nothing more than the latest ripple in its long history. Satellites, such as those in the European Space Agency's Swarm mission, glide around the Earth, measuring the field with delicate precision. Their sensors detect tiny variations in strength and direction. By mapping these signals year after year, scientists can watch the magnetic field evolve almost in real time. They observe the paths of the magnetic poles as they drift. They follow the wave-like patterns that circle the planet, caused by movements deep within the core, and they monitor regions like the South Atlantic anomaly, noting how it stretches or contracts through each passing decade. These measurements help create a detailed picture of the magnetic field's present state. They also allow researchers to compare modern changes with those preserved in ancient rocks, frozen ice, and the carbon stored in tree rings. Through this comparison, they can see the field not as a fixed barrier, but as a living and shifting force, shaped by cycles far older than humanity. For now, the weakening field poses no threat to daily life. The atmosphere remains thick and protective. The field, though changing, still deflects cosmic radiation effectively. But the story unfolding today reminds us that the magnetic field is part of an ongoing dance between the deep Earth and the vastness of space. It shifts because the core beneath our feet never stops moving. It changes because the Earth itself is alive with heat and motion. The present weakening, modest as it is, offers a moment to reflect on the continuity of this ancient force. The same shield that once flickered during the Laschamps Excursion now adjusts itself again, shifting gently as the Earth turns. And just as the trees, the ice, and the stones recorded the changes of the past, our satellites and instruments now hold the memory of this new chapter, watching quietly as the magnetic field continues its slow, graceful evolution. If the Earth's magnetic field were to weaken again in the distant future, slipping into a state of deep instability like it did during the Laschamps period, the world beneath that changing shield would feel the effects in ways both familiar and entirely new. Life would continue, just as it did before, but the way our modern society is woven together makes us far more sensitive to the quiet forces that drift through the space around our planet. We rely on machines that listen to signals from the sky. We depend on networks built from delicate electronics. And high above the atmosphere, countless satellites turn in their long, silent orbits, guiding systems that millions of people use every day. If the magnetic field weakened significantly, solar radiation that is usually bent away from Earth could slip deeper into the magnetosphere. The atmosphere would remain our greatest shield, thick and steadfast, but the thin line of technology floating above it would become more vulnerable. Satellites, which are built from fragile instruments and quiet circuits, could feel the increased touch of charged particles. Many of these satellites carry sensors that help with weather forecasting, climate monitoring, global mapping, and communication. Some provide the timing signals used by financial systems and global trade networks. Others guide airplanes. Still others allow ships to navigate across oceans without losing their course. The global positioning system, which threads signals through the sky, depends on stable conditions in the upper atmosphere. If the magnetic field weakened and solar storms reached deeper into that region, the atmosphere could become more turbulent with ionized particles. GPS signals could scatter or bend. Navigation systems on phones, aircraft, and ships might drift or become less precise. Even small errors in timing can ripple across systems that rely on exact synchronization. In an age when transportation, agriculture, communication, and emergency response rely on satellite navigation, this would be one of the earliest and most noticeable effects. Communication networks would feel these changes as well. Many satellites relay messages between continents or provide internet connections to remote areas. If solar particles reach them more often, their electronics could be disrupted. Some satellites are shielded for normal solar activity, but the weakened field would expose them to more frequent storms and sudden bursts of charged particles. In severe cases, satellites might enter safe mode, temporarily shutting down to protect their systems. If too many storms occurred within a short time, even temporary interruptions could affect global communication, slowing the flow of information that now moves constantly between nations. Aviation would encounter new challenges too. Airplanes flying near the poles already adjust their routes during strong solar storms because high altitude flights are exposed to more radiation in those regions. If the magnetic field weakened, the boundary between safe and unsafe air routes could shift. Pilots might need to avoid certain pathways during solar events, rerouting planes across different latitudes. This would not make flying dangerous in the dramatic sense, but it could reshape patterns of travel, cause delays, or increase the time needed for certain long-distance flights. Communication between airplanes and ground stations could also become less reliable in the upper atmosphere during strong solar activity, requiring new systems to ensure safety. Power grids on the ground, though shielded by the atmosphere, could experience indirect effects. When solar storms disturb the magnetic field, they can induce electrical currents in long metal structures, such as power lines. These currents are usually small, but during powerful solar events, they can grow strong enough to overload transformers. In a world with a weakened magnetic field, these induced currents could become more common. Grid operators would need to monitor their systems closely, ready to disconnect certain lines temporarily to protect critical infrastructure. Yet the story of a future collapse is not one of silent catastrophe. It is a story of awareness. Unlike early humans and Neanderthals, we can see the magnetic field's behavior through satellites, observatories, and sensitive instruments. Scientists track the drift of the poles with remarkable accuracy. They measure changes in the strength of the field across continents and oceans. They build models that simulate the motion of molten iron deep within the core, giving us glimpses into patterns that unfold over centuries. If a significant weakening began, we would see the signs long before they reached dangerous levels. Ground-based observatories would detect the shifts. Satellites like those in the Swarm mission would feel the drift. Data from these tools would allow researchers to forecast how the field might evolve. Power grids could be reinforced. Satellites could be shielded or redesigned. Navigation systems could be adjusted. Airplanes could be rerouted. Plans could be set into motion slowly, with time to adapt. The greatest difference between the ancient world and today lies in our ability to prepare. A future collapse of the magnetic field would unfold gradually, giving us decades or centuries to adjust, to strengthen our structures, and to redesign the systems that orbit above us. Life at ground level would continue with only gentle changes, shielded by the atmosphere that has protected the Earth for billions of years. It is only the fragile, intricate web of modern technology that would need careful tending. The magnetic field has reversed many times. It has weakened, shifted, and reformed. At every turn, life has endured. Now, for the first time in Earth's long history, a species exists that can watch these changes unfold, understand their causes, and prepare for whatever comes next. The invisible shield that surrounds our world is ancient, alive with motion, and still changing. And as it moves through its slow rhythms, we continue to watch, measure, and learn beneath the quiet arc of its protection. As we look back across the long arc of time to the centuries shaped by the Laschamps Excursion, the contrast between that ancient world and the one we inhabit now becomes quietly clear. The magnetic field weakened then, just as it is weakening now, but the consequences unfolded in very different landscapes. The beings who walked the earth during that distant age lived close to the ground, guided by the rhythm of seasons and the behavior of animals. They depended on fire, shelter, and the knowledge passed through generations. Their vulnerability was biological. Ours, today, is largely technological. During the Laschamps period, the weakened magnetic field let more cosmic radiation into the atmosphere. This changed the chemistry of the sky, shifted temperatures in subtle ways, and painted the heavens with red and green auroras that stretched far beyond the poles. It created pressures that touched every form of life, but those pressures were slow, gentle, and spread thinly across centuries. Early humans and Neanderthals had no machines to protect, no wires that hummed with electricity, no satellites tracing paths above the atmosphere. Their concerns remained rooted in food, shelter, and survival through winter. Life then endured the changes as part of the natural fabric of existence. Plants continued to grow, drawing altered air into their leaves. Animals adapted to cooler regions or changed their ranges. Humans migrated, sheltered, and adjusted their hunting grounds. The challenge came not from a single overwhelming force, but from small shifts that stacked themselves quietly over time. The biological world was touched by radiation, climate shifts, and weakened protection, yet it absorbed these changes with a resilience built over millions of years. In our era, the vulnerability has shifted away from bodies and toward the systems we have built. The atmosphere still protects us, just as it did before, and the magnetic field still bends much of the sun's energy aside. But the networks that form the backbone of modern life stand closer to the edge. They reach upward into the region where the Earth's shield begins to thin, relying on calm space weather to function smoothly. If the magnetic field weakened as dramatically today as it did during the Lashamps period, our greatest risks would not be to our health, but to our technology. Satellites could fail, navigation systems could drift, power grids could feel the touch of electrical currents carried through the ground. Aircraft might avoid certain routes. These challenges would unfold not as sudden disaster, but as a steady strain on the infrastructures that keep modern society connected. A future collapse of the magnetic field would be a test of technology rather than a test of biology. Yet one thread connects the two eras: resilience. The Earth has endured countless reversals, weakenings, and magnetic wanderings. Life has adapted through each one. Forests have stretched across continents, then retreated when ice returned. Rivers have carved new paths. Species have risen and faded. Through it all, the planet continued its slow turning, and the magnetic field found its balance again. We, too, stand within that long story. Although our systems can be delicate, we are no longer silent witnesses to the changes in the magnetic field. Modern science allows us to measure the faintest shifts. Satellites record the drift of the poles with precise instruments. Ground observatories watch the strength of the field rise and fall across continents. Scientists build models that simulate the molten currents inside the core, giving us glimpses into patterns that once remained hidden. We do not simply endure change, we anticipate it. The Laschamps Excursion teaches us that the magnetic field can falter, that the atmosphere can shift, and that life will continue regardless. But it also teaches us something quieter, something often overlooked. Even when the planet faced a weakened shield, it did not lose its ability to recover. The field strengthened again. The sky calmed. The climate settled into new rhythms. What seemed like a moment of cosmic vulnerability became another chapter in the story of a planet that has always held the ability to heal itself. Our modern world is different, but the lesson remains the same. A weakened field would challenge us, but it would not break us. With time, preparation, and understanding, society could adapt just as ancient life did. The difference lies in our ability to foresee, to protect, and to guide our tools through the turbulence that might come. In the end, the Laschamps event is a reminder not of fragility, but of endurance. The Earth has weathered forces far greater than those we fear today. Beneath every shift in the magnetic field lies the steady heartbeat of the planet, carrying life forward through every era, every reversal, and every moment of change. Far above the thin blue line of our atmosphere, in the deep quiet of space, countless particles travel across the universe with a speed and energy that defy everyday imagination. These particles, drifting through the galaxy long before the Earth formed, are what scientists call cosmic rays. They are ancient travelers, born in the hearts of exploding stars, in the violent rotations of distant galaxies, and in places so energetic that even light struggles to escape. They move silently through the void, passing through planets, dust clouds, and starlight as if the universe were a vast open sea. Cosmic rays are not rays in the ordinary sense. They are tiny fragments of atoms, mostly protons, some helium nuclei, and a small assortment of heavier particles. Each one carries extraordinary energy. When they approach the Earth, most are deflected by the magnetic field, guided away long before they touch the atmosphere. But when the magnetic shield weakens or shifts, as it did during the Laschamps Excursion, more of these particles find their way downward, and when they strike the upper layers of the atmosphere, they set off a cascade of reactions that ripple quietly through the air. When a cosmic ray enters the atmosphere, it collides with molecules like nitrogen and oxygen that float miles above the ground. These collisions are powerful enough to break apart atoms. The fragments fly outward, creating showers of new particles that scatter in all directions. Some move deeper into the atmosphere, others glance away. A few interact with atoms in ways that leave behind rare forms of elements, known as isotopes. These isotopes are not created in large quantities, and they are not harmful in the amounts that reach the Earth's surface, but they leave a chemical fingerprint that can be traced through time. Two of the most important isotopes created by cosmic rays are beryllium-10 and carbon-14. Their stories begin in the high sky, where the air is thin and cold. When a cosmic particle breaks apart an oxygen or nitrogen atom, the fragments can sometimes rearrange themselves into beryllium-10. This new isotope forms only in the atmosphere, never in the Earth's crust. Tiny grains of it drift downward and become trapped in snow that later freezes into ice. Over thousands of years, the layers of ice stack like pages, preserving the rise and fall of beryllium-10 production as the magnetic field waxes and wanes. Carbon-14 is formed in a similar but gentler way. When cosmic rays strike nitrogen in the atmosphere, some collisions turn nitrogen atoms into carbon. This carbon becomes part of carbon dioxide, joining the swirl of gases that move through the sky. Plants breathe this carbon through their leaves, drawing it into their trunks and branches. Animals eat the plants, carrying the carbon further. Because carbon-14 decays slowly, it acts like a tiny clock inside every organism that absorbs it. When trees grow, each ring they add is a small window into the chemistry of the air that surrounded them. These isotopes reveal the quiet influence of cosmic rays across Earth's history. During times when the magnetic field is strong, fewer cosmic rays reach the atmosphere and the production of isotopes declines. During times of weakening, the opposite occurs. The Lashamps period showed a dramatic rise in beryllium-10 and carbon-14, a sign that cosmic rays were entering the atmosphere more easily and interacting more frequently with the molecules they found there. But the influence of cosmic rays does not end with isotopes. Their interactions shape the atmosphere in deeper, more subtle ways. When they break apart molecules in the upper air, They create charged particles that can affect how water vapor clings to dust grains. These microscopic changes can influence how clouds form, how they reflect sunlight, and how they drift through the sky. Clouds play a delicate role in regulating the Earth's temperature. They cool by reflecting sunlight. They warm by trapping heat. Even small shifts in their behavior can influence climate patterns over long periods. During the Laschamps Excursion, when the magnetic field weakened significantly, more cosmic rays slipped into the atmosphere. Their presence likely altered cloud cover in certain regions, contributing to the shifting temperatures recorded in ice cores and sediments. These changes were not dramatic like storms or volcanic eruptions. They were quiet, persistent, and woven into the natural cycles of the planet. Even today, cosmic rays continue to shape the atmosphere in subtle ways. As the Earth moves through the solar system, the Sun's activity rises and falls in cycles lasting about 11 years. When the Sun is active, its wind pushes many cosmic rays away from the Earth. When the Sun calms, more cosmic rays slip through, altering isotopes and atmospheric chemistry. This rhythm has been repeating for as long as the Earth has existed, and it continues now, unnoticed by most, yet recorded faithfully in the ice, the trees, and even in the particles that reach the ground. Cosmic rays remind us that the Earth is not isolated. It is part of a larger cosmic environment, shaped not only by its own inner heat, but also by the invisible currents of energy that flow between stars. These particles, born in distant explosions and drifting across the galaxy for millions of years, influence our atmosphere with every quiet collision. They help us understand the history of the magnetic field, the timing of ancient events, and the delicate balance between the Earth and the universe around it. In every ring of a tree, in every layer of polar ice, they have left a trace of their long journey through space, a whisper of the deep cosmos written softly into the story of our world. High above the surface of the Earth, in a layer of sky so thin and distant that it feels almost separate from the world below, the ozone forms a fragile shield. It drifts through the upper atmosphere like a pale veil, absorbing the harshest ultraviolet rays from the sun long before they can reach the ground. When the magnetic field is strong and the flow of cosmic particles is held safely at bay, the ozone layer remains steady and protective. But during times when the field weakens, as it did during the long centuries of the Lashamps period, this delicate shield may have been touched in ways that left lasting echoes across life on Earth. When cosmic rays slip deeper into the atmosphere, they collide with the molecules they encounter. These collisions set off small chains of reactions, breaking apart the bonds that hold oxygen molecules together. Some of these reactions reduce ozone, creating short-lived chemicals that interfere with its ability to rebuild. Over time, a weakened magnetic field can encourage more of these interactions, slowly thinning the protective layer that filters ultraviolet light. The change would not have been sudden or dramatic. It would have unfolded gradually, almost invisibly, woven into the natural breathing of the sky. If the ozone thinned even slightly during the Laschamps Excursion, the Earth beneath it would have experienced higher levels of ultraviolet radiation. This increase would not have burned landscapes or scorched the air. Instead, it would have touched life in subtle, cumulative ways. Plants might have grown with thicker leaves, adjusting to shield their cells. The skins of animals may have carried more protective pigments. Species already accustomed to strong sunlight would have continued with ease, but others living in regions with softer light may have adapted with new colors, thicker fur, or changes in behavior. In ancient ecosystems, adaptation often leaves traces in unexpected places. Fossils sometimes preserve hints of pigmentation in feathers or skin. Even though these hints are faint, they can reveal patterns of change. Some researchers have wondered whether shifts in ultraviolet levels during the Laschamps period encouraged the rise of stronger pigments in certain species. Birds may have grown darker feathers in some regions. Mammals might have evolved richer tones in their fur. Pigments such as melanin offer natural protection against ultraviolet radiation. They absorb sunlight and prevent damage to DNA. When ultraviolet levels rise, species with more melanin often have an advantage. In the plant world, the influence of increased ultraviolet light may also have been felt. Plants often produce compounds that shield their tissues from radiation. During times of higher ultraviolet exposure, these protective compounds can increase. Some ancient pollen grains, preserved in sediments, show variations in their chemical signatures that might reflect the conditions of the sky above. These changes are small, like whispers in the fossil record, but they suggest that the atmosphere's shifting chemistry touched every level of life. From the largest mammals to the tiniest grains of pollen drifting on the wind, certain insects may have adapted as well. Their exoskeletons contain pigments that protect them from sunlight, and some species adjust their activity patterns in response to ultraviolet intensity. In periods when the ozone layer thins, insects sometimes shift their behavior, seeking shade more often or becoming more active at dusk. Though we cannot watch the behavior of insects that lived 42,000 years ago, we can study the patterns of their descendants, whose habits still respond to changes in sunlight today. For early humans and Neanderthals, the effects of increased ultraviolet exposure would have been felt on their skin. Melanin, the pigment that creates variation in human skin color, serves as a natural shield against ultraviolet light. It absorbs energy and prevents deeper layers of skin from being damaged. As groups moved across different regions, their pigmentation shifted in response to local sunlight. If ultraviolet levels rose during the weakened magnetic field, these pressures may have influenced the gradual patterns of pigmentation in ancient populations. Those living in sunnier areas might have developed deeper tones, while those in colder or cloudier regions kept lighter skin to help absorb more sunlight for vitamin D production. The balance between these forces is complex, shaped by climate, diet, and time. Cosmic rays offered only one quiet influence among many, but their presence added another thread to the tapestry of evolutionary change. What makes the ozone connection compelling is not the scale of its effects, but the way it touches every part of the natural world. A slight thinning of the ozone layer changes the light that reaches the surface. That light influences the growth of plants, the behavior of animals, the color of feathers and fur, and even the chemistry of ancient trees. Across thousands of years, these small influences shape the patterns of life, and yet the ozone never vanished. It thinned in places and strengthened again as the magnetic field recovered. The atmosphere adapted to the shifting conditions, just as the Earth's magnetic shield eventually regained its strength. Life beneath it continued, adjusting quietly as it always has. The Lashamps period reminds us that even the most delicate parts of our world can respond to cosmic changes with resilience. The sky above us is not static. It is shaped by forces that stretch across the galaxy, and the life beneath that sky carries the memory of those changes in its colors, its chemistry, and its long evolutionary story. Across the ancient world, long before writing took shape and long before stories were carried on paper or screens, early humans left their memories on cave walls. These paintings, carved or brushed onto stone, are among the oldest records of human thought. They show animals with curved horns, horses with flowing manes, and handprints pressed softly as if someone wanted to say, "I was here." For generations, people believed these images were mostly scenes of daily life, hunts, and rituals. But as scientists have studied the magnetic collapse of the Lashamps period, a new idea has begun to rise quietly among researchers. It suggests that some of these ancient paintings might capture something far larger than hunts or animals. They might contain echoes of the sky itself. During the weakened field of the Lashamps event, the atmosphere would have glowed with auroras spread across the world. These auroras would not have stayed near the poles. They may have stretched over Africa, Asia, Australia, and parts of Europe. Imagine families gathered near cave entrances, watching red and green lights ripple across the night. The glow would have been slow and smooth, drifting like curtains. To early humans, such lights would seem mysterious, powerful, and impossible to ignore. The sky itself may have appeared alive, and ancient people, with their keen awareness of the world around them, may have tried to capture what they saw. Some cave paintings contain shapes that do not match animals or familiar earthly forms. They show patterns that look like branching lines, radiating spirals, or clusters of repeating marks. These strange shapes have led some researchers to wonder if they might represent the lights of the sky. Modern observers who study plasma, the glowing matter that creates auroras, note that certain aurora patterns form shapes similar to those found in ancient art. Curtains of light sometimes twist into spirals or undulating lines during strong magnetic disturbances. Streaks of brightness can gather into clusters or dots, forming patterns that could easily spark the imagination of someone witnessing them for the first time. The pigments used in these paintings deepen the mystery. Early humans often chose red, black, yellow, and white natural colors made from minerals or charcoal. Red ochre, for example, appears in many cave systems around the world. Its warm tone resembles the deep red glow that auroras can produce during strong solar activity. Black manganese or charcoal appears in thin lines that could reflect the dark shapes seen between streaks of light in the night sky. While these pigments were chosen primarily for practical reasons, such as availability and durability, their presence in images that resemble atmospheric phenomena invites curiosity. Some specific caves hold imagery that has drawn attention for this reason. In the caves of Europe, certain panels contain clusters of dots arranged with careful intention. Researchers have suggested that these dot clusters resemble plasma shapes seen during intense aurora storms. When cosmic particles interact with atmospheric molecules, they can create rippling spots of light that blink softly in groups. These lights are difficult to describe in words, yet easy to imagine as a pattern of dots painted by a witness sitting at the mouth of a cave, working by firelight and trying to preserve the memory of a sky transformed. Other caves show long, vertical strokes that some believe resemble picket fence auroras, a type of display where narrow beams of light rise toward the stars like glowing pillars. These patterns do not appear often in the natural world, but they can emerge when the magnetosphere is disturbed, allowing charged particles to rain down along magnetic field lines. If such lights shone during the Lashamps weakening, they could have stretched across regions where early humans lived. The simple lines painted on stone could reflect the shape of those pillars, stylized through the eyes of the artists. There are also swirling patterns that resemble what plasma physicists call auroral curls, where the lights twist into soft loops. These curves sometimes appear in cave art beside animal figures, as if the painters wanted to place creatures of the earth beside shapes of the sky. Perhaps these images were symbolic. Perhaps they were literal memories. Or perhaps they blended meaning and observation in a way that is difficult for us to separate today. The idea that some ancient art could record auroras is still a young theory. Many researchers believe the patterns represent spiritual symbols, tracking marks, or artistic expression unrelated to the sky. Cave paintings carry many layers of meaning, and early humans lived rich lives filled with culture, ritual, and imagination. The images may reflect their inner world as much as the natural world around them. Yet the timing of some paintings, created near the era of the Peng magnetic collapse, invites a gentle possibility. If the sky glowed with unusual colors for centuries, it is natural to wonder whether the people who lived beneath that glow found ways to record what they saw. Even if only a few of these images were inspired by the shifting sky, their presence reminds us of a simple truth. Early humans were not separate from the natural world. They watched it closely, lived within its rhythms, and responded to its changes with art, memory, and wonder. The caves became their libraries, the walls became their canvas, and in those quiet spaces, lit by fire and shadow, traces of the ancient sky may still linger, preserved in minerals and stone. Whether these marks represent animals, symbols, or lights from a forgotten night, they offer us a bridge to the past, a chance to stand where ancient people stood and imagine the world as they saw it, touched gently by the glow of a sky transformed. Long before humans pressed their stories into cave walls, and long before trees recorded changes in the sky through delicate chemical traces, the earth itself was already writing its own memory. It wrote not with ink or pigment, but with stone. Every mountain range, every cooled lava bed, every layer of oceanic crust holds a quiet record of the magnetic field as it existed at the moment those rocks formed. These geological memories stretch back hundreds of millions of years, forming a timeline far older than any living witness. To understand how rocks become storytellers of the magnetic field, imagine a river of molten lava flowing from a volcano. While the lava remains hot, the tiny grains of iron inside it drift freely, pointing in all directions like countless wandering compass needles. But as the lava cools and solidifies, these grains lock into place. Each grain freezes in the direction of the magnetic field present at that exact moment. When the lava hardens completely, the safer grains become tiny magnets pointing toward the ancient north. They remain locked in that direction for as long as the rock survives, sometimes millions of years, carrying the memory of a magnetic world that no longer exists. These frozen directions are known as magnetic signatures. They appear in volcanic rocks along continents, in basalt flows on the seafloor, and in layers of sediment built up by lakes and rivers. Each signature is a small snapshot of the magnetic field as it shifted, weakened, reversed, or strengthened. By reading these signatures, scientists can piece together the long and complicated history of the Earth's magnetism. On continents, ancient lava flows form long sequences that stretch across valleys and mountains. When scientists examine these flows, they often find that the magnetic directions do not match the current orientation of the field. In some layers, the iron grains tilt toward the south instead of the north. In others, they lean sideways, as if the procand poles were wandering across the sky. These patterns show that reversals have happened many times. The magnetic field has flipped from north to south and back again, sometimes quickly by geological standards, sometimes after long periods of slow change. Sedimentary rocks tell similar stories, though in a softer voice. When mud settles onto the floor of a lake or ocean, it carries with it tiny iron-rich grains that align gently with the magnetic field. As more mud accumulates above them, these grains become pressed into place. The layers they form capture a continuous record of the field's shifting behavior. Unlike lava, which freezes a single moment in time, sediments preserve smooth transitions, showing how the magnetic field wandered between full strength, confusion, and reversal. The ocean floor holds one of the most striking records of all. Along the mid-ocean ridges, new crust forms as magma rises from below and spreads outward in both directions. As this molten rock cools, it captures the magnetic direction of the field exactly like any other lava flow. Over millions of years, the spreading crust creates long parallel stripes of magnetized rock that run across the ocean basins. Some stripes point toward a normal north, others point toward a reverse north. Together, they form a pattern that looks almost like a barcode stretching across the seafloor. These magnetic stripes are symmetrical on both sides of the ridges. This symmetry shows that the field reversed many times and that the ocean floor grew in steady pulses. When scientists first discovered this pattern in the 1960s, it became one of the strongest pieces of evidence for plate tectonics. The Earth's crust was not fixed in place. It was moving, spreading, and carrying its magnetic memories with it. As continents drifted over millions of years, they carried their own magnetic records from poles to equator and back again. Rocks that formed near ancient poles now sit near the tropics. Those that formed near the equator now rest in high latitudes. By studying these rocks, scientists can reconstruct the wanderings of entire continents. This process, known as paleomagnetism, reveals maps of the ancient Earth. It shows where mountain ranges once stood, where oceans opened and closed, and where ice sheets advanced and retreated. But the most remarkable part of this story is how consistent the geological memories are across the planet. Rocks from Africa tell the same sequence of magnetic reversals as rocks from North America. Basalt flows in India record the same ancient flips as those in Australia. The ocean floor patterns in the Atlantic match those in the Pacific. It is as if the entire world kept a synchronized diary, each page written in stone, each line echoing the same global shifts in the magnetic field. These geological records also reveal that reversals do not follow a predictable rhythm. Some occurred after long, calm stretches lasting tens of millions of years. Others happened more frequently. The patterns show no repeating cycle, only the natural variability of a restless core that stirs and changes over deep time. Yet, through all these changes, the field has always returned, reorganizing itself into a stable orientation that lasts until the next reversal begins. If we could walk through time by touching rocks, we would trace a path through valleys shaped by ancient lava, across seaside cliffs cut from old ocean crust, and along mountain ridges built from continents that once lay far apart. Each stone would carry a whisper of the magnetic field that guided it into place. And together, those whispers would form a story that spans the entire history of our planet. In these quiet magnetic memories, the Earth reveals not only its past, but its resilience. The field has faltered, reversed, and revived countless times. And through each shift, the stone beneath our feet has captured the echoes, waiting patiently for someone to listen. As we move farther from the ancient stones and the memories they hold, the story of Earth's magnetic field begins to unfold on a larger canvas. The field that surrounds our planet is not unique in the universe, yet it is far from ordinary. To understand just how fortunate we are to live beneath this invisible shield, it helps to look outward toward our neighbors in the solar system. Each world tells a different tale of magnetism, atmosphere, and survival. Together, they frame Earth's story within a wider perspective, one shaped not only by molten metal and cosmic particles, but by the delicate balance that allows life to breathe. When we stand on Earth and imagine the magnetic field stretching far into space, it feels almost natural, as if every planet should have something similar. But in truth, Earth is unusual. Our magnetic field extends tens of thousands of kilometers into space. It forms a bubble that bends solar winds around us, gently guiding charged particles toward the poles. This shield gives our atmosphere time to settle, thicken, and evolve. It helps keep oceans in their basins and allows delicate molecules like oxygen and nitrogen to remain close to the surface. Without it, the sun would strip these gases away grain by grain. But this magnetic cocoon is not the rule in our solar system. It is closer to an exception. Take Mars, for example. Today, it is a quiet world, cold, dry, wrapped in a thin atmosphere that could never support large bodies of water. But billions of years ago, Mars told a very different story. Its surface once held flowing rivers that carved winding valleys, lakes gathered in craters, and minerals formed only in the presence of long-standing water. For such water to remain stable, Mars must have once had a thicker atmosphere, and for that atmosphere to survive the sun's wind, it must have had something like a magnetic field. Evidence suggests that Mars did indeed have a magnetic field early in its history. Its crust still carries faint magnetic patches, remnants of an ancient time when molten metal moved deep below the surface. But the Martian core cooled more quickly than Earth's. Over time, the churning motions that once created a magnetic field began to slow. Eventually, they weakened so much that the field collapsed altogether. Without magnetism to deflect the solar wind, Mars stood bare before the Sunday solar particles began to chip at the atmosphere. They brushed against the upper layers and carried particles away into space. Slowly, silently, the air thinned. As the atmosphere weakened, water escaped into the cold void. Rivers dried, lakes vanished, and the planet transformed from a warm, watery world into the desert-like landscape we see today. The loss of its magnetic field began a chain of changes that reshaped the entire planet, leaving behind a reminder of what happens when a world loses its shield. Venus offers a different kind of lesson. Larger and closer to Earth in size, Venus lacks a magnetic field not because it cooled too quickly, but because its internal rotation and structure do not create the conditions necessary for a strong, flowing core. Without such a field, Venus stands exposed to the Sunday, yet its atmosphere remains incredibly thick, far denser than Earth's. Instead of losing its air, Venus gained an overwhelming amount of heat-trapping gases. The sun stripped away lighter molecules long ago, leaving heavy carbon dioxide behind. This gas built up until the planet reached a runaway greenhouse state. Today, the surface of Venus is hot enough to melt metal, and its sky is filled with clouds of acid. Mars and Venus sit on opposite ends of a spectrum, one losing its air and water, the other drowning beneath a heavy blanket of heat and pressure. Earth, somehow, found a middle path. Its magnetic field helped it hold on to an atmosphere dense enough to support oceans, yet not so thick that it trapped unbearable heat. This balance has allowed life to flourish for billions of years. As we observe these neighboring worlds, a quiet question rises. Could our future mirror theirs? What would happen if Earth's core ever stopped moving? If the molten iron beneath our feet lost its swirling energy, the magnetic field would begin to fade. Without the shield, solar winds would press against the atmosphere more directly. Over long spans of time, they could strip air from the upper layers. The process would be slow, almost unnoticeable on a human timescale, but significant across ages. Yet Earth carries something Mars did not. Our planet is larger. It cools more slowly. The heat trapped at the core continues to churn metal in deep currents that show no sign of stopping soon. We also have a thick atmosphere and active geological cycles that help stabilize climate. These combined forces make Earth far more resistant to drastic loss. Still, the comparison reminds us how delicate the balance truly is. The magnetic field beneath us is not permanent. It shifts. It weakens. It restores itself. Its presence gives us a rare and fortunate place in the solar system, a world where oceans can remain liquid and air can support breathing life. Looking outward to Mars and Venus, we see what can happen when that balance fades. Looking inward to Earth, We see how lucky we are that the core continues to turn, sending its silent protection out into space and giving our world the stability to thrive. Deep beneath our feet, far below the crust and mantle, where mountains rise and oceans move, the true engine of Earth turns in endless darkness. It is a place we can never visit, a world of liquid iron and extreme pressure, where heat flows like a silent current and metal behaves like water. Yet even from the surface, scientists have learned to listen to this hidden realm. With every tremor, every ripple of seismic energy, the core whispers clues about its movement. And as we gather those clues, a new picture has begun to emerge, one that reveals a restless, shifting heart that shapes the magnetic field we depend on. At the center of this hidden world lies the solid inner core, a sphere made mostly of iron, packed tightly enough to resist melting despite its immense heat. Surrounding it is the vast outer core, a deep ocean of molten metal that churns and circulates with slow but powerful motion. This liquid iron moves under the influence of heat rising from below and the rotation of the earth above. Together, these forces create patterns that twist, swirl, and fold in ways as intricate as weather systems in the sky. In recent years, researchers studying the core have begun to uncover hints that it does not simply spin in harmony with the rest of the planet. Instead, the inner core may rotate slightly faster, a phenomenon known as superrotation. This difference is incredibly small, almost impossible to detect directly, yet it hints at a dynamic dance unfolding beneath our feet. If the inner core rotates at a different speed from the mantle and crust, it could generate subtle variations in the magnetic field. These variations might help explain why the field drifts, strengthens, or weakens over time. But the dance is not only about rotation. The outer core behaves like an enormous ocean of metal, and oceans are rarely calm. Seismic readings suggest that waves travel through this liquid iron, moving in large arcs around the inner core. Some waves flow smoothly, while others appear turbulent. Magnetic turbulence, a pattern of swirling currents that form when liquid metal changes speed or direction, may influence how the magnetic field fluctuates. These swirling currents act like tangled threads, twisting the lines of the magnetic field and causing subtle variations that ripple outward through the entire planet. Detecting these waves is a delicate task. When earthquakes occur, they release bursts of energy that travel through the earth. Some of this energy bends downward, reaching the outer core before rising back to the surface. As the waves pass through different layers, their speed and direction change. By measuring these tiny changes, scientists can reconstruct what the waves encountered. It is a little like shining a flashlight into a dark room and studying the reflected glimmers to learn what objects lie inside. Through this method, seismologists have found patterns that hint at large structures within the core. Some regions seem to move more quickly than others. Some waves slow down or curve as if passing through patches of different density or temperature. These shifts suggest that the outer core is not uniform. Instead, it may contain slow rising plumes, swirling eddies, and channels of hotter or cooler metal. Each feature contributes to the complex motion that generates the magnetic field. The idea of turbulence inside the core may seem surprising, but it fits with what we know about fluids under extreme conditions. Just as winds in the atmosphere can twist into cyclones, and currents in the ocean can form spiraling gyres, the movement of molten iron can create waves and vortices that fluctuate over time. These fluctuations may help explain why the Earth's magnetic poles wander, or why the field sometimes weakens and recovers. The magnetic field is not a rigid structure. It is a living, shifting consequence of the core's hidden movements. Some studies even suggest that waves called torsional oscillations sweep through the outer core every few years. These waves are subtle pulses that pass from one side of the core to the other, slightly speeding up or slowing down the rotation of the inner core. Their presence could act as a stabilizing force, helping the magnetic field reorganize itself whenever it becomes chaotic. If these waves strengthen or weaken, the field might respond in ways we see at the surface. Although the core remains unreachable, scientists continue to refine their understanding through improved seismic instruments and computer models. With each new discovery, the complexity of the core becomes clearer. It is not a simple engine turning steadily in the dark. It is a vast, dynamic sea of metal shaped by heat, rotation, and gravity. Its movements influence the magnetic field, and in turn, the magnetic field influences everything from compass directions to atmospheric processes. When we imagine the Earth from afar, we see oceans, forests, and clouds. But beneath all of that lies this quiet dance, a continuous motion that began long before life emerged and will continue far into the future. The core is the heartbeat of the planet, steady yet full of subtle rhythms, and though we may never see it directly, we feel its presence every day in the protective field that wraps our world in safety. Far beneath the waves, in the quiet darkness where sunlight never reaches, the ocean floor holds a secret written in long, sweeping bands of stone. These bands stretch for thousands of kilometers across the seafloor, forming patterns so regular and so striking that scientists once compared them to the stripes of a zebra. Each stripe carries a magnetic memory from the moment it formed, a memory of whether the Earth's magnetic field pointed north or south at that time. Together, these stripes reveal one of the most elegant pieces of evidence that the magnetic field has reversed many times throughout the planet's long history. To understand these stripes, imagine standing at the center of a mid-ocean ridge. These ridges are immense underwater mountain chains where new oceanic crust is born. Heat rises from deep within the Earth, lifting the seafloor and splitting it apart. Molten rock rises through the cracks and spreads outward. As it reaches the cold ocean water, it cools rapidly and hardens into basalt, a dark volcanic rock. This process happens slowly but steadily, adding fresh crust to the edges of the ocean floor year after year. Inside this cooling rock, tiny grains of iron float freely while the lava remains hot. As the rock solidifies, these grains align with the direction of the Earth's magnetic field, just like compass needles settling into place. They become locked within the stone, preserving the magnetic direction at that moment. If the field points north, the grains align north. If it points south, they tilt south instead. Over hundreds of thousands of years, as the crust continues to spread, new layers form on both sides of the ridge. Each new band carries its own magnetic direction. When scientists first mapped these directions, they discovered a pattern they did not expect. The magnetic stripes mirrored each other perfectly on both sides of the ridge. A strip of normal magnetism appeared on the east side of a ridge, and a matching strip of normal magnetism appeared on the west side. Next to those, a strip with reversed magnetism appeared, then another normal one, then another reversed one, all in perfect symmetry. It looked as if the ocean floor had grown like a tree trunk, adding rings that alternated direction with each shift in the magnetic field. The discovery of these stripes was a turning point in understanding Earth's past. It proved that the magnetic field had flipped many times, and that these flips were global events. It also confirmed that the ocean floor was spreading outward from the ridges, carrying its magnetic memories with it. This spreading helped reshape our understanding of how continents move. Continents, though massive and seemingly eternal, are not anchored in place. They sit atop plates of crust that drift slowly across the surface of the Earth. These plates slide, collide, and break apart over millions of years. As they move, they carry the magnetic signatures within their rocks, preserving the ancient directions of the field like pages in a drifting book. When scientists study rocks on different continents, they sometimes find that the magnetic directions do not match the current orientation of the poles. Instead, the rocks may point toward a pole that no longer exists in that location. These mismatches reveal how far continents have wandered. For example, rocks in Africa may show a magnetic north that once lay near the equator. Rocks in North America may point toward a pole that once drifted across the Pacific. By comparing these directions with those found in other places, scientists can reconstruct the ancient positions of continents. The result is a kind of magnetic map of deep time. It shows where land masses once lay, how they collided to form mountains, and how oceans opened and closed around them. The zebra stripes on the seafloor also provide a timeline of reversals. Each band represents a period of stable magnetism. When the field flips, the next band preserves the new direction. By analyzing the thickness of each stripe and comparing it with radioactive dating of seafloor samples, scientists have created a detailed record of magnetic reversals stretching back millions of years. Some stripes are wide, suggesting long periods when the field held steady. Others are narrow, indicating quick flips or short intervals of stability. The pattern is irregular, unpredictable, and full of surprises, reflecting the chaotic nature of the molten core that generates the field. These magnetic records reveal that reversals are neither rare nor catastrophic for the planet. They are simply part of Earth's deep rhythms, unfolding across timescales far longer than a human life. Each reversal leaves its mark in stone, carried by continents and preserved in ocean crust, waiting for someone to uncover it. When we look at these stripes, we see more than geological data. We see evidence that the Earth has a long memory, one written not in words but in magnetic signatures. We see continents drifting like slow-moving rafts, carrying traces of ancient poles as they travel. We see an ocean floor that grows and shifts, keeping a perfect record of every reversal and every moment when the magnetic field changed direction. These patterns tell a story of a planet in motion, a world shaped by hidden forces that ripple from the core to the crust. And in these quiet magnetic lines, preserved beneath the sea, we find yet another reminder that the Earth is alive with movement, history, and quiet transformation, all unfolding beneath our feet. Deep inside the Earth, where darkness has weight and heat moves like a slow-rising tide, the magnetic field is born from motion. The molten iron of the outer core swirls in vast currents, rising and sinking as heat escapes toward the mantle above. These currents do not move in perfect loops. They twist, fold, and bend, shaped by the rotation of the planet and the uneven flow of heat from the inner core. When these motions fall into rhythm, the magnetic field becomes steady. When the currents become tangled, the field weakens and begins to shift, sometimes flipping its poles entirely. Yet no matter how chaotic the patterns become, the core always finds a way back to stability. To imagine how the field repairs itself after a reversal, picture the inner workings of the core as an enormous pot of swirling liquid metal. When the flow is calm and organized, the field is strong. When the flow grows tangled or disrupted, the field wobbles, weakens, or changes direction. During a reversal, the internal currents become confused. Lines of magnetic force twist into new shapes. Regions of the field scatter, canceling one another out. At the surface, the field grows thin and disordered. This state does not last forever. It is simply a transition. As the chaos settles, convection slowly begins to reorganize. Hot iron rises from the inner core, cools slightly, then sinks again. These motions form patterns that repeat over long periods, almost like slow breathing cycles beneath the planet's crust. With time, These currents reestablish a stable direction. It does not happen suddenly. It unfolds across centuries. The magnetic field regrows in small steps. Weak regions strengthen, scattered patches merge, and lines of force realign with increasing clarity. This recovery is delicate. Some parts of the field may stabilize sooner than others. Near the equator, the field might remain weak while the poles regain strength. The wandering magnetic north may drift in wide arcs before settling into a new home, but the direction eventually becomes steady again. The field becomes whole. The planet finds balance. The recovery after a reversal is so slow that generations of early humans would have noticed almost nothing. They would not see the moment when the field reached its lowest point or the moment when it strengthened again. For them, the changes were simply another quiet shift in the world around them, folded into the long breath of time. Even today, with satellites watching every part of the field, the recovery remains subtle. It might take thousands of years before stability fully returns after a major reversal. Scientists studying ancient rocks and seafloor stripes have traced many such recoveries. Some reversals took less than 10,000 years to settle, others stretched across much longer spans. A few events were incomplete, with the field drifting toward a flip before circling back into its original direction. These near reversals show that the core can come close to chaos and still guide itself home without fully switching north and south. The key to this resilience is convection. No matter how complicated the motion becomes, heat continues to rise from the inner core. That simple upward movement acts like a guide, encouraging the molten iron to settle into patterns that support a stable magnetic field. Even when turbulence dominates, the deep heat never stops flowing. As long as this heat escapes, the outer core will continue to stir and the field will continue to rebuild. Computer simulations show that the process resembles a storm fading into calm weather. At first, currents in the outer core swirl unpredictably, pushing magnetic lines into strange directions. Regions of the field weaken or vanish, but as the currents find their rhythm again, the storm fades. Streams of molten iron settle into broad, looping motions that reinforce one another. The magnetic field grows clearer and stronger, spreading across the planet like a slowly brightening dawn. This resilience becomes even clearer when viewed in the context of the Earth's long history. The magnetic field has reversed hundreds of times. Some reversals were complete, some were partial, some lasted brief moments in geological terms, others stretched across long epochs. Yet the field always returned. It may have thinned or flickered, but it never disappeared entirely. The Earth's core has always found equilibrium again. Even during the Lashamps event, when the field weakened to only a small fraction of its usual strength, the core eventually reorganized. Convection patterns stabilized. The field recovered. The planet continued its rotation, wrapped once more in its protective magnetic cocoon. When we think about the future, this long record offers comfort. The magnetic field may weaken again. It may drift or wobble. Centuries of slow change may unfold, but the deep processes that drive the field are patient. They move with the steadiness of time itself. They adjust, correct, and restore balance in ways that stretch far beyond a human lifetime. The story of magnetic reversals is not a story of collapse. It is a story of renewal, a story of a planet that has found equilibrium again and again, guided by the quiet dance of molten iron hidden far beneath the surface. In this deep and ancient rhythm, the Earth reveals its enduring strength, showing that even in moments of turbulence, stability always returns. Life on Earth has always been shaped by forces that move quietly in the background. Some of these forces drift across the sky in the form of sunlight or storms. Others rise and fall in oceans and currents. But one of the most persistent guides to life's long story is something almost impossible to see. It is the magnetic field, the silent shield that wraps around the Earth and bends the harshness of space into gentler forms. Without this protection, the earliest steps toward complexity might never have taken place. And the countless branches of evolution, from ancient microbes to forests and animals, may have followed very different paths. To imagine the world without the magnetic field, picture the planet bathed constantly in charged particles from the sun and cosmic rays from deep space. These particles carry enough energy to break apart delicate molecules, including the fragile threads of DNA. Early life, which depended on stable environments and simple chemistry, needed time to grow and adapt. It needed a refuge where its molecules could survive long enough to change, divide, and create new forms. The magnetic field offered that refuge. As the field pushed solar particles aside, the upper atmosphere became a shield of its own. Molecules collided in high layers, scattering energy in directions that spared the surface. Beneath this quiet protection, simple cells began their slow and patient work. They learned to gather energy from sunlight, to build stronger structures, and to divide into copies of themselves. Over enough time, some cells combined forces, joining together in groups that would eventually become the ancestors of every plant and animal alive today. This delicate rise in complexity needed stability. Yet, the magnetic field did not remain constant. It wandered, weakened, and reversed many times. During these transitions, more radiation likely reached the surface. The increase was not enough to destroy life, but it may have nudged evolution in subtle ways. Radiation can damage DNA. Sometimes the damage goes nowhere. Sometimes it harms an organism. But sometimes, once in a great while, a small change opens a new path. Evolution thrives on variation. The more variation that appears within a population, the more opportunities there are for new traits to rise and spread. Some scientists have wondered whether magnetic reversals, with their temporary weakening of the shield, contributed to moments when life diversified more quickly, not because the reversals forced change, but because they allowed small sparks of radiation to dance through the atmosphere in ways that encouraged new genetic combinations. In the ancient oceans, where early animals drifted in layered currents, bursts of mutation may have helped create fresh traits. Perhaps a creature developed a new pigment that protected it from ultraviolet sunlight. Perhaps another gained a slightly different pattern of movement or metabolism. These tiny shifts, multiplied across millions of individuals, could push evolution in unexpected directions. Over vast spans of time, such changes accumulate and reshape entire ecosystems. Later, as life grew more complex, the magnetic field continued to play its supporting role. Land plants depended on a stable climate to spread their green canopies across the continents. Animals needed breathable air, water that stayed in its basins, and an atmosphere thick enough to protect delicate tissues. The magnetic field helped preserve all these conditions by shielding the planet from atmospheric loss. If the sun had stripped too much air away, the Earth might have followed a path closer to Mars, where cold winds sweep across a barren landscape with no protection from space. The magnetic field also gave the Earth space to hold on to its oceans. Without that shield, energetic particles would have chipped at the upper atmosphere, pulling water molecules apart and allowing hydrogen to escape into the void. Over billions of years, the oceans might have thinned, leaving fewer places for life to thrive. With the shield in place, water gathered into deep basins, tides rose and fell, coastlines shifted, and life had room to expand. There is also the subtle influence of magnetic cues on the behavior of animals. Many species today, from birds to salmon to sea turtles, rely on the magnetic field to navigate long distances. they sense its lines like an invisible map. Such abilities may have evolved early in Earth's history. Creatures that could detect magnetic clues might find better feeding grounds, safer nesting sites, or more reliable migration routes. These advantages would help their offspring survive, weaving the magnetic field into their evolutionary story in a more direct way. Still, the most profound influence of the magnetic field lies in the stability it offers. Life flourishes when conditions remain steady enough for generations to grow and adapt. The magnetic field has helped preserve that steadiness for billions of years. Even when it weakened or reversed, the changes were slow and gentle compared to the long sweep of evolutionary time. Life had room to adjust. Mutations might have increased slightly, but not so much that ecosystems collapsed. This balance between protection and variation may have been a quiet engine driving the rise of complexity. As we look across the history of life, from ancient microbes to towering mammals, the magnetic field remains a constant presence. It does not guide evolution directly. It does not choose which species rise or fall. Instead, it offers a stable stage on which life can perform its slow and intricate dance. It holds back the harshest forces of space, allowing delicate molecules to persist long enough to create new forms. And through its moments of weakness and recovery, it adds small opportunities for change, moments when evolution might take unexpected steps. In this way, the magnetic field is both guardian and silent collaborator. It has sheltered the planet since life began, giving complexity the time and space it needed to unfold. And as long as the core continues to move, shaping the field above it, this quiet guidance will continue into the ages still to come. As we drift from the deep history of magnetic reversals into the present day, the question that quietly rises is simple. With all our instruments, satellites, computers, and knowledge, can we see another collapse coming? The magnetic field has weakened and recovered many times before, always on its own silent schedule. Now, with scientists watching every shift, we stand in a rare moment where the Earth's invisible behavior is no longer hidden. Yet, even with this careful attention, the future remains wrapped in gentle uncertainty. Today, the magnetic field is tracked through a network of observatories scattered across the world. Some sit on quiet islands, far from interference. Others stand in forests, deserts, or icy plains. Each observatory measures the strength and direction of the field, sending its data into global records that stretch back for more than a century. These measurements show how the field drifts each year, how it strengthens or weakens, and how the magnetic poles wander across the Arctic. But even these ground stations are only part of the story. To see the field in its full, three-dimensional shape, scientists look upward, high above the Earth, drifting through the calm darkness of low orbit. A group of satellites watches the magnetic field from above. Among them is the European Space Agency's Swarm mission, a trio of satellites that circles the planet like quiet guardians. They measure the magnetic field with instruments so sensitive they can detect subtle shifts in strength, small disturbances in direction, and faint patterns rising from the core. Swarm does not only observe the field that surrounds us, it also separates the magnetic signatures that come from different parts of the planet. Some magnetic signals rise from the crust, locked into rocks long ago. Others drift in the upper atmosphere where charged particles gather. Still others flow from the core itself, shaping the global field we depend on. By teasing apart these layers, Swarm allows scientists to watch the movements of the core indirectly, seeing how its molten iron shifts and stirs. Through these observations, scientists have traced a slow weakening of the magnetic field over the past 2 centuries. The field has lost about 1/10 of its strength in that time. This weakening is uneven, strongest in a region known as the South Atlantic Anomaly. Over South America and parts of the southern Atlantic Ocean, the field dips to unusually low levels. Satellites passing over this region often encounter radiation that slips deeper into the atmosphere than it should. Engineers must build special protections for the instruments that fly through it. Some people have wondered whether this anomaly could be an early sign of another collapse. Researchers studying the anomaly use swarm data to map how it changes from year to year. They watch it grow, shift, and divide into smaller patches. These changes are clues to the movements of the core beneath, just as ripples on a pond reveal the motion of water below the surface. These magnetic ripples hint at deeper processes hidden far beneath our feet. Yet, despite all this data, predicting the next collapse remains one of the great challenges of Earth science. The core is too distant to observe directly, and its motions are too complex to model perfectly. Scientists see patterns, but they cannot be certain which patterns signal an approaching reversal and which simply reflect the natural wandering of the field. Computer models can simulate thousands of years of magnetic behavior, but each simulation unfolds differently, revealing the many possible futures the field might follow. The truth is that magnetic reversals do not follow a schedule. Some occurred after long periods of stability. Others happened only a short time after the previous one. There is no repeating cycle, no predictable countdown. The field has flipped hundreds of times across Earth's history, yet the gaps between reversals vary wildly. Some were separated by 1 million years, others by tens of millions. One long stretch passed more than 20 million years without a flip at all. Because of this irregularity, predictions today range from comforting to unsettling. Some scientists believe the field will not collapse again for many thousands of years. Others suggest we may already be in the early stages of a long weakening phase that could lead to a reversal sooner than we expect. The uncertainty does not mean chaos. It simply reflects the complexity of the molten currents that generate the field. Even if a reversal is approaching, it will unfold slowly. The field would weaken over centuries, not days. Satellites would have time to adjust. Power grids could be fortified. Communication systems could be redesigned. Unlike ancient humans who watched the sky change without understanding why, we have tools, foresight, and the ability to prepare. What the data truly shows is not danger, but motion, a field that wanders, breathes, and drifts, a core that dances in slow, unpredictable rhythms, a planet that has been doing this for billions of years. In the end, predicting the next collapse may never be exact, but watching the field today gives us insight that no generation before us ever had. We may not know when the next reversal will come, but we understand that the magnetic field is alive with movement, and in that movement lies the quiet story of a planet that continues to change, just as it always has. If we step quietly into the rhythm of the present day, a gentle truth begins to unfold. Modern life, with all its speed and comfort, floats on a structure so delicate that most people never pause to notice it. We live beneath an invisible shield, one we cannot touch or see, yet everything around us depends on it. It steadies our climate, protects our atmosphere, and guards the signals that thread through the air. It guides birds across oceans, keeps satellites alive above the clouds, and shelters every breath we take. For all our technologies, achievements, and dreams, we remain tethered to the same magnetic field our ancestors lived under when the sky glowed red in ancient nights. Today, the world is woven together by signals that cross continents in the blink of an eye. A single moment carries countless invisible threads. Messages flow through fiber cables under the sea, leap through wireless towers, or glide through satellites orbiting far above. These satellites rely on calm conditions in the space around Earth. They expect predictable levels of radiation and steady magnetic forces. When the field weakens, even slightly, these conditions change. A satellite's instruments are sensitive. A burst of charged particles from the sun can scatter through its electronics, causing glitches or temporary blind spots. Engineers design them with protections, yet the magnetic field remains their quiet first line of defense. Without it, the solar wind would reach them more fiercely, washing over their delicate components. Navigation systems that guide ships and aircraft depend on this stability. Even the soft voice of a phone call or the precise time that keeps financial systems synchronized rides on the calm created by Earth's magnetic shield. On the ground, the dependence continues. Communication lines stretch across countries. Power grids hum at the edges of cities. These networks are strong in appearance, but they are vulnerable to the subtle influence of space, weather. A powerful solar storm, if not deflected by the magnetic field, could send electrical currents surging through long lines of metal. These surges may overwhelm transformers or disrupt distribution networks. In a world where everything is connected, a single interruption could ripple far beyond the place where it begins. Climate stability, too, is held gently within the influence of the magnetic field. The field keeps the upper atmosphere from thinning too quickly. It shields the molecules that make the air breathable. It allows water to remain on the surface instead of drifting slowly into space. Without this protection, the atmosphere would gradually erode, changing the balance that makes Earth's climate gentle enough for life. We often speak of greenhouse gases and oceans warming, yet beneath those concerns lies this deeper foundation. A quiet shield has sheltered our atmosphere for billions of years, giving life room to evolve and endure. For all this dependence, most people go through their days, giving the magnetic field no thought at all. We trust the lights to turn on, the satellites to stay in orbit, and the seasons to follow their ancient paths. Yet beneath that trust lies a fragility that ancient humans did not share. When the field weakened during the Lashamps event, early people had no satellites to protect, no electrical grids to guard, no network of flight paths spanning the globe. Their resilience was older and simpler. They lived close to the land, shaped by its rhythms. A shift in the sky might have inspired fear or awe, but it did not threaten the foundation of their world. Modern systems, for all their brilliance, carry a kind of delicacy. A single storm in space can ripple downward through orbiting machines and into the wires that power cities. A change in magnetic strength can influence navigation tools that guide airplanes or ships. Even the smallest adjustments to satellite timing can shift global communication networks. These systems form the spine of contemporary life, yet they lean quietly on the magnetic field, trusting it to hold. This contrast between ancient resilience and modern vulnerability does not diminish our achievements. Instead, it offers a gentle reminder. For every step we have taken into the digital age, we remain connected to forces older than humanity itself. We depend on a shield forged by the motion of molten iron deep beneath our feet, a shield born long before the first breath of life. The field requires no maintenance, no fuel, no repair. It flows from the Earth's core as naturally as tides rise and fall. When we think about the future, this invisible dependence becomes part of a deeper reflection. The magnetic field may waver, it may wander, it may weaken for a time, but its protection has endured across countless ages, and life has always found ways to continue beneath its shifting strength. Our modern systems may need reinforcement or adaptation, yet the Earth itself continues. Its slow and steady turning, wrapped in a shield that has shaped every chapter of life's story. In this quiet realization, we see our place in a much larger pattern. The magnetic field holds us gently, guiding particles, protecting oceans, and guarding the air we breathe, while we build our fragile wonders upon its strength. And beneath every signal and circuit, the ancient shield continues its silent watch. As our long journey draws gently toward its end, we return to a truth that has been with us from the very beginning. Beneath everything we have explored, beneath the changing skies and the wandering poles, beneath the cold winds that once swept across mammoth plains and the glowing curtains of light that startled ancient eyes, there has always been a quiet guardian. It asks nothing, it announces nothing. It waits below our feet, shaped by motions older than memory, and surrounds our world with a soft, invisible shelter. The magnetic field is not something most people ever think about. We cannot touch it in our hands or see it drifting above us. Yet it threads its presence through every breath of air, every wave on the ocean, and every spark of life that grows beneath the Sunday. It is as old as Earth itself, born in the deep rhythm of molten iron swirling in the planet's center. Those swirling currents create an unseen force that stretches far beyond the sky, forming a protective bubble that holds back the storms of space. Through these chapters, we have wandered into one of the rare moments when that guardian faltered. The Lashamps event, a fleeting collapse 42,000 years ago, revealed just how delicate this balance can be. For a short slice of time, the shield weakened so deeply that the sky shimmered with lights from horizon to horizon. Cosmic particles pressed closer to the ground, the atmosphere trembled, the world grew colder in places. Life felt the shift in subtle and sometimes harsh ways. Yet the earth continued to turn, the field found its strength again, and life endured. This memory, locked into ice, stone, and the quiet chemistry of ancient air, stands as a gentle reminder of the planet's long story. It shows us that forces we cannot see shape every part of our world. It shows us that even the most constant protections can waver, and it shows us that the earth itself holds a resilience deeper than any single storm. Looking back across the ages, it is humbling to realize how easily these hidden rhythms weave into our lives. We walk through our days with quiet trust that the air will stay thick, that the sun will shine safely, and that the seasons will keep their familiar pace. Satellites orbit above us, electricity hums through wires, navigation signals sweep across oceans. But all of these rely on the same shield that once protected Neanderthals, warming their hands by ancient fires, and the same shield that watched mammoths cross frozen valleys under skies touched by drifting lights. In the Laschamps event, we saw the rare moment when that rhythm faltered. Today, the magnetic field still shifts and sways. It weakens in some regions and strengthens in others. Over long spans of time, it may reverse entirely, just as it has done countless times before. But through all of this, it remains the quiet force that makes Earth the world we know. And so, we find ourselves here, at the end of this gentle exploration, holding an appreciation that is soft and steady. The shield beneath our lives has guarded the planet through fire and ice, through drifting continents, and through the rise and fall of species. It asks for no gratitude. It simply continues, shaped by the deep heartbeat of the Earth's core. As night settles again and the world grows quiet, we can carry with us the calm understanding that this shield still surrounds us. It still bends the wind of the Sunday. It still guards the air. It still protects the life that covers oceans and forests and cities. The magnetic field will shift again one day. But for now, the shield still holds, protecting life as it always has.